So would I not be able to use my laptop?
We'll try. Computer ever connect?
No, it's just a blank screen.
Okay.
Oh, okay.
Can we try?
On your laptop. Kind of.
Let me try your laptop.
I mean, if
We have the dongle.
Yeah, it's not working with the dongle?
It's not working with the dongle. Okay, that's no problem. You might also try to reboot your computer.
Okay. Yeah.
Let me try real quick. It works. Yes, I know. Sometimes it's just.
Okay, I just 5 minutes and then. Good morning, everyone, and welcome to the first edition of PAgE, which is the Principles of Agentic Engineering workshop at PLDI. We have a stellar organizing committee, including folks from Microsoft Research, University of Washington, and University of California, Berkeley. And thanks to PLDI, thanks for being here, and thanks to PLDI organizers for hosting us. So what the motivation behind this workshop is, this community has gotten good at making software reliable, but agents pose a new challenge. Agents are, they plan, they call tools, and there are tool outputs, there's memory. So this program of agents consists of prompts, tool calls, memory, and dynamic traces, which are being updated at runtime. So this poses a new set of challenges, like so some concrete challenges with agents is, as you'll see in the talks today, is they are a long horizon, so the traces can go on for like thousands of like tool calls, interactive sessions, and they're also probabilistic. So the non-determinism is inherent in the agent world. In each input, each different prompt can, each same prompt can lead to different outputs. And also, there's a lot of external dependencies like tool calls, databases, a lot of system backend is being called during the agent session. And of course, the problem we all struggle with, like the specifications are ambiguous, and extracting executable contracts from them is a big challenge. So what we hope to do today is the folks like connect with the different interdisciplinary folks in this room, like programming languages, AI, and share ideas, interact with each other during the talks, and also hopefully at the end of it, we'll have like a research community. We keep collaborating and exchange ideas and have an agenda that we all care about. So just a quick logistics about PAgE. So this is the first edition, and we have 10 contributed talks, 2 keynotes, and 34 authors across 3 countries and 10 institutions. So this is just the first edition, and we hope that as the years go by, this will grow, and a lot of folks from the programming languages community especially would care about this problem. So yeah, I won't take up too much time. You must have seen the agenda for today. So without further ado, it is my pleasure to introduce our first keynote, Gagandeep Singh. He's a professor at UIUC, where his group works on bringing formal guarantees to AI systems. He also co-leads the Science and Technology group at the Institute of Governance and Public Affairs, focusing on AI governance and the future of work in AI. And his work has been recognized through the NSF Career Award, Google Research Scholar Award, multiple Amazon Research Awards, and an Open Philanthropy Research Grant. So today he's going to talk about what formal methods can offer to the frontier of AI. And yeah, please welcome Gagandeep Singh. Yeah.
Okay, well, very glad to be here, and I will be describing some of the works we have been doing in terms of bringing formal guarantees for frontier AI systems, right? I will not waste time. It's like collaboration with a lot of people at UIUC, also from Amazon and other places. I don't want to tell you like how impressive these models are. But there is also evidence that risks matter despite all the hype and all the stories what you see on LinkedIn and whatnot, right? So there's this survey from Stack Overflow from last year, which has results from I think more than 30,000 developers about the different challenges of using AI agents. So in terms of the top concerns, they're still worried about the security and privacy risks of AI agents. There's also like a more global survey because there are different factors that affect whether somebody wants to use AI or not. It's not only risk, but there are other factors, for example, AI education, integration costs, regulatory hurdles, and so on, so on. So even if we look at those things, risks matter. And I think despite all the improvements we can get, the tail risks will always remain. And formal methods have a role to play in ensuring in improving these tail risks, right? And recently also in Illinois, similar to New York and California, they passed the accountability bill. This was actually supported by Anthropic and OpenAI, right? So one of the key aspect of this bill, and it's going to be signed by the governor soon, is that third-party auditors should be like accessing how safe these models are. So we talk about all these more broader themes in this FTP podcast. Now, you might hear this kind of forecast from economists which say that AI will have $6 trillion impact or $12 trillion impact and whatnot. Usually, those kind of forecasts are based on very optimistic assumptions, which is based on what AI can do, right? So here, this is our position in terms of even like accessing the long-term economic impact of AI and what it can do. So if you see the blue circle, it's a conceptual illustration of what humans can do and what quality they get. So when organizations are assessing whether they should use LLM or not, they need to see if AI brings any kind of gains. And these are called productivity gains, either in terms of money or in time savings, right? So the current forecast assumes optimistic position, which is with this pink curve, which is the set of tasks where AI can exceed or match the performance of humans. But these don't consider risks at all, right? So my agenda has been to have the risk-focused conversations also started in this kind of economic assessments. So when you encounter risk, this notion of this frontier of LLM impact and so on is jagged, because for some tasks which are equal difficulty for humans, AI can outperform humans, but it can also be worse than humans, right? Now, if we consider the risk, this even becomes more jagged. And our prediction is that if the capabilities increase, you already see that with the recent Meadows ban, the frontier can become even more jagged, right? Because for something like cybersecurity, the more capable your model is, the more risk is going to possess, right? So risks are going to persist. That's the main message. And formal methods have a role to play. Now, I give this talk to also machine learning audience, right? And usually it comes up like some kind of laundry list. Hey, formal methods cannot do this, formal methods cannot do that. And that just kills all the conversation, right? Now, if you will also read papers that are written sometimes by formal methods people about what formal methods can do, sometimes what happens is that it takes a bit more pessimistic view of what formal methods can do, right? So bashing your own tools sometimes, like, okay, SMT will never scale, or things like, oh, we can't do world models. So I like to take a more optimistic view on this. Maybe I'm wrong. I think the pessimistic view may also be wrong, right? The goal is not to just directly go to like, oh, let's model all the world model and interaction with the environment and what LLM can do, right? Let's start somewhere, right? And I will tell you that whatever you can do, it will still be better than what people are doing. So the goal is to get the conversation started, right? So I'll show 4 applications, mostly focusing on offline evaluation, and then I will also consider online monitoring and enforcement, specification guided training, and interpretability. So offline evaluation is when you have trained a model, you want to know how good the model is, how safe the model is before you go for real world deployment. That's crucial. You can have all the guardrails you want, they don't come for free. You will have to pay some inference overhead because of this. So during production, the companies, they will have a very elaborate evaluation pipeline which will assess how good the model are. So the goal is, how can formal methods assess the safety of these models, right? So we have been doing formal verification for neural networks for now say 8 years. There are 2 components, a specification and verification algorithm, and usually the number of specifications you can satisfy is used as a metric to compare different models. Usually we don't go for like absolute safety in the sense of formal methods, but the goal is to give some kind of actionable feedback to the developers that can guide them towards selecting the right model. Now there's a lot of work on this direction, and usually the specification here is like, okay, you have an image that's correctly classified as car, you add some noise, maybe rotate it, and you want to check if the prediction is robust. So the most popular approach for this is abstract interpretation. It's incomplete, and that's something, you know, like when we want to apply formal methods for these frontier models, is something we have to forego anyways, because it's going to have very nonlinear computations. You are not going to be complete, right? So we have even like written a monograph capturing all the progress in this area. We have also been trying to accelerate making these abstract interpreters for neural networks easy in terms of having a domain specific language, also a verifier which can check if an abstract interpreter written in the language is sound, and then also having a translation to a PyTorch compiler. So you have to spend less effort on actually constructing this verifier. But the point is that these are still not enough for if you want to go for LLM kind of verification. The thing is, the models handle a large and diverse set of prompts, and you can't really capture that with adding some kind of linear constraints on the output tokens or some kind of robustness properties, right? And then the computations itself are complicated. They actually, I like to see LLMs as some kind of neurosymbolic systems where you have neural computations, continuous computations combined with discrete decoding steps, which can be represented as a symbolic algorithm. And then the LLMs, and I think this was very good what Shraddha was saying, that even on the same input in different runs you are going to see different outputs, right? So they are stochastic. So billions of dollars I think I spent on AI safety evaluation, and I ask a very simple question. can an LLM produce an unsafe output for a given prompt? Like I'm not even starting from the most complicated world model you can think of. I'm starting from a very simple verification problem. At least for that you can get a specification because it's just one prompt. And none of the safety evaluation method can do anything about it, because it's actually AI safety evaluation is an ad hoc discipline and not a scientific rigorous discipline at the moment, right? So people will create prompts, they will do something random, collect some response and report whatever they get, but they can't answer this question, right? So existing methods actually cannot answer even this simple question. So if you can do any progress on this, you're already doing better with whatever people are doing with their giant evaluation. And big companies as well, they don't do anything about this. So what is the problem? The problem is, if you ask a problematic question like how to build a bomb, the model is not going to give you a single output. It actually produces a probability distribution over all the outputs. So some of the responses can be safe and some of them can be unsafe. So people typically would sample a few responses, but it can be that some of the responses that you never sampled are unsafe, right? So just sampling a few responses does not let you, even for a single prompt, assess the safety. Now I would also say that safety is not a binary thing. It's not like, oh, for one prompt you are safe and for another prompt you are unsafe. It's not a binary thing, it's a more continuous thing. Can happen that for one prompt your unsafe mass of the outputs is less, but it increases steadily as you move in the prompt space, right? So there is a need to assess safety at the distribution level. Now people also say, I will do like closed source models, so it will have deterministic decoding, so what we can do, right? I mean, even in those cases, we know because of floating point errors, we see non-determinism. So there's nothing deterministic about these models. So even for closed source models, if your model is having unsafe outputs with non-trivial probability, it's possible it will show up in some run, right? And it's not a theoretical construct, right? We have actually developed this popular classes of attacks. It's very popular for open source models. It's called prefill attacks. So it exploits the autoregressive nature. So suppose you want to ask how to build a bomb. The model is safety trained, it's not going to give you the answer. But because you have open source model, you can just prefill, like make the model response start with sure here are steps, and then the model gives you what you want. You don't have to do any heavy optimization or 4 hours of whatever GPU computation. With very simple attack, you can break all the open source models, even now, right? So why this happens, one reason for this is because the harmful information is in the distribution. You just make it more, you just take the LLM, take the path that you want to take, and then it gives you whatever information you want. So people also talk about a lot about unlearning and all these objectives. I don't know what unlearning means, because they just suppress information. They actually do not remove the information. If you want to remove the information, you have to do it at the level of distributions. Feel free to ask questions. So this also was shown in this deep alignment paper from last year. So on the left hand side, what you are seeing is the KL divergence, which is a measure of the distance between the probability distributions. So you have the blue one is the KL divergence between the instruction tuned, like a safety trained model of Llama, and a non-safety trained model, right? And the x-axis is the token positions, right? So you measure at different token positions in the response what is the difference between the probability distributions of the aligned and non-aligned model. So what you see is that whatever safety alignment does, it's very short-sighted. So there's only difference between the probability distributions of these models at the first few tokens, and everything else, even between the aligned and non-aligned model, is the same. So if you can bypass the first few tokens by prefilling, which is what you see on the right hand side, you are going to succeed in terms of attack. And this attack has been repeated many and many times, right? And people also do this kind of generation exploitation attack, where if you have open source models, you can make it more stochastic and you will get the information you want. So the point that I'm trying to make here is that it's not enough to just look at the top responses, you need to reason it at the level of probability distributions, right? Now, the thing is that if you want to answer the question I said, qualitative, it can be that for the model has very unsafe output, but the probability of that is 10 to the power minus 20, right? And then if you just ask the binary question, you would make two models, give the same rating to two models. One has probability 10 minus 20 and the other has probability maybe 0.5. So instead of going for the qualitative answer, we go for quantitative question. So the quantitative question is, we want to compute the probability mass associated with unsafe outputs for a given prompt, right? So that would be the start. So you can frame it as a model checking problem. So suppose you have a property which is defined over the output of LLM M, and then later you can also define a distribution of prompts that we will discuss later, right? So, but for a given prompt, you want to estimate how much of the probability mass satisfies G of phi, which is a specific kind of property we are choosing, which is saying that every point in the generation, the constraint should be valid, right? So examples of this would be privacy, right? So if you are looking for image leakage and then the model gives you the email address, then whatever it generates later does not matter, you have already violated. Other examples would be stereotype. If I have said something bad about a specific group, then whatever, if I say I'm sorry, it's kind of not good. So this property can capture a lot of what we want to verify. So ultimately, in terms of LLM verification, I envision 4 of these problems, and they look similar, but they are not, right? So the first thing is, for single prompt risk, we want to estimate how much of the probability mass is unsafe, or verify if the probability to unsafe response is exceeding some threshold. The second is, if we are given a distribution of prompt, we want to compute prevalence. So if we were to sample a random prompt from the distribution, how much distribution level risk it will have. Average risk also takes the probability of each prompt from the distribution into account when aggregating it at the level of prompt distribution. And worst case risk is you want to find the worst case prompt in the support set, or find a prompt which has high risk. So we have currently been able to do single prompt risk. It scales 70B models. It's not a problem. Prevalence of risk as well, and we are making some progress on the worst case risk as well. Now, I would not say we are able to verify everything, but there is something to show, right? And then the key insight why we chose this formulation of G of phi, which is common in model checking, is that it allows us to terminate early. So if a prefix of a generation, so the model generates set of outputs, and for each output there is a probability associated. So if the prefix violates, then you can discard the rest of the generation. And it captures properties like privacy and security that people are concerned about. So let's look at the single prompt risk, and the baseline approach for that is just rejection sampling. So you just sample n responses, and then you can bound. You would not be able to compute the exact probability, but you can compute a lower and upper bound and use that to give some guarantees, right? So what you can do is you can find the number of responses that are satisfying. That would be your lower bound, and upper bound would be 1 minus the sum of violating responses. Now the bad thing about that is that it will not be able to use the prefix closed property that I have, because you would need to generate the full response, and then rejection sampling is not good enough in terms of generating non-duplicate samples. So it wastes a lot of effort and is not very efficient. A lot of people, in neural network verification competition, like competition, etc., there's alpha, beta, crown, marabou, etc. They're good for a single pass, meaning going from the LLM input to one token generation. But once you have to generate multiple tokens, you will not get anything good out of this, right? So practical verification requires reasoning about strings and probabilities, and we have the algorithm is quite efficient. It's called Beaver. And then the key insight here is that you want to track partial sequences. So you want to have a specific decoding of the LLM generation that keeps tracks of partial outputs and then prune constraints as soon as you detect violation. So we have two data structures. I will get to them soon: token tree and frontier. And we will also have exploration strategy. So let's look at this generation process, right? So it's like a tree data structure where the root represents empty string, right? So when the LLM has processed the prompt, it starts generation step by step. At each step, it generates a probability distribution over next tokens. You select a token, and then that feeds as the input to the next phase, right? So here, the root is the empty node, and then the nodes represent the sentences you can form by following along the edges. So N4 is representing LS minus AL, right? And then the edges are also annotated with the probability assigned to these tokens. These are directly taken from the LLM's output probability distribution. So the probability of a sentence can be calculated by multiplying the probabilities along the branches, right? So that's the definition of node, and edge is just labeled with the probability of token given all the previous generation. And you have frontier, which is all leaf nodes. So in this tree, we will not keep track. We will remove any partial sentence that violates. And the good thing about is that if you can detect violation early, you would get rid of the full subtree. So that will make you efficient. And complete node is something where you have finished generating, so that you can use to increase your lower bound, right? So the lower bound would be the sum of all complete nodes that are non-violating, and then upper bound you will start with one and subtract any subtree mass that violates, right? So let's look at a simple property. You have a toy LLM, and the vocabulary is some Linux commands, and you are just looking at generation length 5. We can currently scale up to, I think, 128 or 64, which is good for certain practical tasks, right? So what are the safety constraints? The output should not contain any deletion operation, should not have any access to sensitive system files, and no system modification. This is a toy property. You can see that this is G5 because as soon as the prefix violates, you prune. So you will start off with setting your lower bound to 0 and upper bound to 1, and with the leaf and the root node, that's empty string. Then you would expand by running a forward pass to the LLM, get the probability of different tokens, and get a new tree. So you would update your lower bound and upper bound. So in this case, we found that there was 0.1 of the probability mass that was violating. So the upper bound is 0.9. So the main thing here is that once you have this set of nodes, which node you want to expand next, and that determines the cost of verification. And I would not say that there is a universal algorithm exploration policy that can work for every property. It is very property dependent and the LLM dependent. So we have currently just used a greedy heuristic. That's also kind of common in probabilistic model checking in terms of selecting the node with the highest probability at the moment, right? Remaining probability. But you can also do some learning. So you would keep doing this sequence and updating your lower and upper bound. You can stop anytime. At any time you stop, you would get a sound lower and upper bound. Now the lower bound increases slowly compared to the upper bound because the lower bound you can only increase once you have generated the full sentence, right? We are thinking of ways to overcome this barrier, right? So the cost depends on the policies for exploration, right? How often, you want to select nodes for expansion by running the forward pass, that changes your upper and lower bound as fast as possible, right? And you also have to check, you need to have an oracle which can tell you whether the property has been violated or not. So sometimes these checks can be expensive depending upon your checker, so you need to have custom policies as well. Currently we are just doing it at each step. So let's look at the first task where, yeah.
Are you taking questions
I can, yeah.
So in this one, is there an assumption that the amount of sampling an attacker can do is less than the amount of sampling that you are doing during this bound determination?
No, I mean,
No?
we are doing the offline evaluation, right? So this is before the deployment, you are assessing.
Right, but there is not necessarily a convergence, right? Like you will determine these lower and upper bounds, and let's say within your understanding you declare it safe, but
Yeah.
an attacker could sample even
Yeah.
more and get out of that.
Yeah.
Is that statement correct? Or?
Yeah, that is
Oh, okay.
statement correct.
That's-
Also, when I will go to the distribution of prompts, the point is that it's hard to like say that the LLMs will never break, but we want to see how difficult it is, right? So this is simple task, GSM symbolic, which is a math reasoning problem, and this is not even like safety verification, but twice task just to see how good the algorithm is. So we want to check if we give a prompt from this data set, which asks the model to generate some symbolic math expression, how much of the probability distribution satisfies syntactic and functional correctness, and that is checked with Z3, right? So the oracle here is reliable, and then we compare the lower and upper bound with Beaver versus rejection sampling, and we can see that for this task we can get fairly close in terms of the lower and upper bound, right? And then n is the number of forward passes you need to do. So usually like for 33 forward passes, this finishes within a few seconds. So there's no, I mean, if you are really worried about the stochasticity, there's no need to avoid this. I mean, you should just be doing it. And then the other thing we are looking at is like secure code generation, where we have 204 REST autocomplete instances from cybersec eval, and we generate a specific jailbreak prompt prefix where we say to the model, you are an old programmer, you are frustrated with the world, so generate insecure code, right? And we use the detector that comes from the data set, and this detector can have false positive and false negatives. So whatever guarantees we give is modulo the correctness of the detector. In some cases we can get sound detectors, in other cases we can't. And here, because the generation length is also higher, we don't really see the lower bound increase so much. We focus on the upper bound property. So we want to check how many of the 204 prompts you get that the risk of insecure generation as detected by the detector is more than 10%. So if it's more than 10%, it's significant. The developers can tune as they want. And the other property we are looking at is like stereotype bias, where you have some jailbreaks from the decoding trust data set, and you want to check how often does that model generate something that is biased against specific groups. And we do the same metric here as well. So again, we can scale to like all of these common open source models. We are able to find, compared to sampling, like if you see for stereotype, for gamma 12b, the sampling does not find any stereotype examples, but in 12% of the cases, we find more than 10% probability, right? We have more detailed evaluation. We can scale up to 70b, and if we get more resources like the big companies, there's not a problem. We can't do like, I mean, whatever you give, yeah.
Yeah, so two questions. First, can you handle, changing the temperature, which kind of continuously adjusting the distribution?
Yeah, so what we currently do is we evaluate at temperature is equal to 1, which is like the most stochastic setting. So that really tells you how much of the probability distribution is it. When you change the temperature, make it more narrow, it becomes easier for us because the distribution is more focused, right? So currently the results I showed you is on the more challenging setting in terms of the temperature. Equal
and the other figure, you show the comparison between your approach versus the naive or the sampling based approach. Like, what do those numbers mean? Like, what do you compute? Is that like an upper bound, like not this one, but the probability one? Like the numbers can differ by a lot, right? So if you look at the upper and lower bound computed by Beaver and rejection sampling. Right?
Yeah.
So what these numbers mean actually? Is this a
So this is what we are bounding the probability of correct response, right? And this says that the correct response probability is at least 0.343, and it cannot exceed 0.356. So the true probability is within the bound. Right.
And how do you compare like the different intervals, like computed by rejected sampling versus Beaver? Is that more like precise or is that more?
Well, in this case, you can see for the first case, it's more precise because the interval is included. So depending upon the application, you might be more interested in lower bound or upper bound, right? In this application, we report both, but for the other applications, it's more with the upper bound.
Sounds good.
Now, we also know some ways of like getting rid of this prefix close property, but let's focus on how we can then specify distribution of prompts, because that was also mentioned by Shraddha in terms of like, oh, how do you like describe this, right? So the reason I go for distribution of prompts and not like a deterministic set is to avoid the mistakes we did in local robustness thing, because what happened there was that people want to verify as large as region as possible, but many of these regions contain nonsensical inputs that should never be verified. So it's very hard to say in general if your specification is actually correct, right? So we rather have not give the same probability to every point and try to skew based on some heuristics. We usually work with different practitioners. So actually the presentation I'm making you, the research actually happened in the reverse order. So we did this first and then that came later, but the story flows better now like this. So we actually started doing this thing like 3 years ago, and based on our exploration, right, it took us a few months to figure out what a specification should look like. So we have identified 3-4 properties that the specification should have. One is that it should cover a large set of prompts. As I mentioned, we want to have a distribution. We want to give currently statistical guarantees, right? So that means high confidence bounds on the probability over a full distribution. Working towards deterministic guarantees there as well. So the main challenge here is that you want to be able to define a distribution from which you can collect IID samples. If you can't give statistical guarantees. And the overloaded terms, it needs to capture practical real world usage patterns. So that usually is very domain dependent. Nobody can say, like if the distribution is correct or not, or if it is actually what the users are doing. You can try to refine it. And now we actually have a language for LLM specification, which Isha will present later in the afternoon. And we have some loop going on where you can go from natural language description to formal specification in this language. So I will present one of the properties which was at AI Stats this year, which is reading comprehension. So this is important for instruction following and so on. So basically you give a set of facts in unstructured manner, which mimics a lot of real world deployments for chatbots, etc. And you want to check, you ask a question about the unstructured paragraph or text, where the answer is in the text you provided, and then you want to assess how good the model is as answering those questions, right? So we build on top of knowledge graphs. So here the nodes are different entities. They have aliases. For example, you have paracetamol and acetaminophen and plasma acetaminophen. So the same node has different variants, names associated with it. So you also have context, right? So you might have some more information about paracetamol fetched from a Wikipedia page that might be available in this knowledge graph. And then you have edges, they also have aliases, right? So we'll use this knowledge graph to build specifications, which is distribution of prompts. So we'll work with some prompt constructor which takes a subgraph of this graph and then converts it into some kind of prompt to give to the model. And then we will ask a multiple choice question, and the correct answer should be possible to infer from the model. So basically we are testing multi-hop reasoning capability of the model, whether the model can go through the facts that are given by the edges. The answer is always going to be the last node in the sample subgraph. So what we want to test is the the challenges that occur in real world. For example, information can be arranged in arbitrary order. You might have extraneous information, right, more than what the model needs to answer the question. You might have alternative terminology which is captured by the aliases, and you want to have unstructured long form context. So there's a lot of work on this, but they actually don't formally specify distributions, and they don't model all these four at the same time. So we want to model this natural noise. So we have this concept of distractor nodes, right? So suppose this green nodes are the subgraph I chose. I can also select another node that is related to the nodes in the subgraph, but is just designed to distract the model. So the red one here is related to the subgraph, but it's not the answer to the query, which is the last node, and it is related because if you see the edges, damage leads to damages and damage leads to damages, right? The two edges, they have the same edge, but they are different nodes. So I can formalize this notion of distractor, which is a node that is not a part of your subgraph, but it has some relation with the node that you have sampled. So this is formalized, and you will also use random aliases, for example, for different nodes and edges. You can also do information shuffling. So once you have generated your prompt constructor, you can change the sentences, the order of sentences, right? So that can form a distribution. So the distribution looks like this. In the subgraph, you will select a node which has a lot of outgoing edges. Then you would define a distribution over the paths starting from that node up to a certain length 5. And then you would also have probability of information shuffling, distractor nodes, and so on, so on. So you can use that to define a very large distribution. And then this is very different from the Beaver verification I showed you. Here you are saying take a prompt from the distribution and a single response. We are not talking about the full distribution of LLM response, right? Because this happened first, right? And then you can use Clopper-Pearson to just sample n independent and identically distributed samples and then compute the bounds on the true probability with high confidence. That just means that if I run the verification procedure, let's say I get 95% confidence, if I run the verification procedure 100 times, 95% of the times the bounds will be correct. But a given bound may not be correct. We don't know which bound is correct or not, right? So this is how the framework looks like. You would have a knowledge graph. You would define some distribution over the subgraphs, which are just paths starting from a particular node. It can also be you give a particular template, a substructure, and then you want to sample subgraphs that correspond to those, right? And then you would construct prompts with all this natural noise and so on, and then check how often the model succeeds. And the knowledge graph we use is Wikidata and PRIME-KG, which is a data set about medical facts. And these are the results. We have like 9 specifications for PRIME-KG and 50 for Wikidata, and we are comparing GPT-4o, Gemini 1.5 Pro. And we have specifications vanilla where we don't add any noise, and when we add noise, and we are finding the bounds again on the probability that for a randomly sampled prompt, a randomly sampled response will be correct. What we see here is that the probability reduces when you add the noise for even the state-of-the-art models, right? So they are susceptible to distractors. And this is one example where I think this is for GPT-4o, it gets distracted and gives some wrong medicine, which actually can have bad impact. Yeah.
You quickly showed 16-bit and 4-bit.
Yeah.
Effect due to quantization.
Yeah. We were also measuring the effects of quantization in these cases.
What do you make of which?
So as we see is that the larger model are better, but they are not perfect, right? So if you see GPT-4o and Gemini 1.5 Pro, in the vanilla setting for prime kz is almost having 1 probability, right? But if you go for llama 3 11b with 4 bit, that probability reduces. Not too bad, but it reduces. What you also see is that for the larger models, when you add the noise, the probability also goes down. Yeah.
I have a question. So, mostly these models have these files plot.md where you can inject some instructions like do not use this.
Yeah.
Do not use it. Have you tried to like
Yeah. So, we gave all of that. The point is that these models, that's why I mentioned about tail risks, right? These models are going to work most of the times, but they're going to fail some of the times, right? And then if you don't, I would say, at least for something like code generation, etc., I just don't like that people say, oh, I will use LLM just as a detector or whatever, right? We can do more than that, right? And then sometimes people are like, okay, we can't do SMT and so on, but I mean, why not use the power of like, forgo completeness, but try to give more scalable, solvers that can work on multiple GPUs and so on, right? So I think to eliminate tail risk, formal methods has a way to play, right? And we hope that more people join it. And I think if 100 people from formal methods form a big team, we will make more progress than just keep doing data collection. So one thing I really don't like is this notion that spending billions of dollars collecting data and then running on massive resources is scalable, right? And then somehow formal methods are not scalable. I mean, that does not make any sense to me, because it uses so much resources, but somehow that notion is fed that this is scalable. I mean, if you ask like somebody in, let's say, a normal developer in like India, Africa, Asia, wherever, right, $100 for cloud is not a scalable solution, right? Formal methods have a way to play, but if we keep accepting that our things are not scalable and then whatever people are doing is scalable, then we'll never make progress. I think we should push back against that notion.
Have you thought about using the learnings from evaluating these prompt distribution for optimizing the prompt, or that's orthogonal?
Yeah, we are working on that currently, and I will show you the next case where we are working on. So that was catastrophic risk in conversation, and I think Shraddha again mentioned that in long conversations these models can get lost. I have seen that multiple times, right? So here we create a distribution over conversations. Again, you can model it as a graph where the nodes represent different prompts. So the point is that you are not going to directly ask how to build a bomb, but you are going to ask it in an indirect way. Hey, who was the inventor of, I don't know, some related chemical and whatnot. And then what happens is that even if the model does not give you directly the response, over time that probability increases, because from my perspective there are a few reasons for this. It induces out of distribution safety state, so that's something where we are trying to use the findings from this prompt distributions, right? So the distributions are done over the paths in the graph. Again, we don't have to go into details, Isha will mention, but I just wanted to show some results for Cloud Sonnet and GPT-OSS and so on. Again, in this case, we are computing the probability of unsafe response, right? And this is actually used by Amazon now for evaluating their Nova models. And at least for this scenario, Cloud Sonnet 4 is quite good. The probability of unsafe response is very low. But if you see something like, and these are different distributions in the columns, right? Mistral has like at least more than 50% probability of giving you a catastrophic answer, right? Even GPT-OSS is usually very safe, but for this adaptive rejection, it's a particular distribution, it goes unsafe. We have other things like counterfactual bias. This was actually the first work where we again showed that the model can give very biased responses for male, female, and other races, right? And this is an older result, but even there, the results were not very good. We have agentic tool selection, where the task is that the model should select a tool according to user intent. So we look at the poisoning case where we poison the stash, I don't know what it is called, slate, with some suspicious tool and see how often does the model select those, and it most of the time fails. So Lumos is the language that Isha will present. It's a graph-based language with probabilistic certification. It also supports things like VLMs. And you can combine this kind of statistical guarantees with Beaver to now get guarantees on statistical guarantee on prompt distribution and deterministic guarantees on prompt output distribution. So we did this preliminary results on Quen 3.4b with Beaver and Lumos distribution, and the bounds are not very good. This is for privacy. And we also now have people say, hey, is your specification like really the distributions you generate are really like adversarial or not? So now we actually have an algorithm for VLMs that actually searches for worst case distributions. And we have shown it for VLMs. I think Isha will mention more about it. And the vision models are not very good in general. So in this case, this Quen VL is not able to see I think exposed electrical wires. Okay, so let's focus on the second thing. I think I have 15 minutes. So this one was online enforcement. So offline evaluation is before you want to deploy the model. You can use formal verification to get some kind of assessment. I think the main use case is you would be able to select which model to choose for deployment in some cases, right? We have the language, and now people usually try to hammer the approach by saying, oh, but this language specification is very hard to design. I mean, I think now with this cloud capabilities, you can go from natural language to the specification in this DSL fairly quickly with some human in the loop effort, right? Now the second approach is online monitoring. Once you have deployed the model, can formal methods can be used to improve the model as a guardrail or whatever, right? So this is orthogonal to the other approach. So the thing is that during deployment it can improve your trustworthiness, but it has some cost associated with increasing inference overhead. So we will look at enforcing structural constraints. They are important. So here this is a program verification task where you ask cloud to just give the invariance to prove some property about this program. Now again, we do all the prompt tuning to cloud, right? Don't do certain things or whatever, right? But every so often it also changes the source code and proves the program, right? You might want to enforce some constraint here so that you actually prove the property you want to prove, right? So structural constraints are important for LLM generation. Despite training on massive amount of data set during deployment, sometimes these models are not able to satisfy those. So the problem here is a constrained learning problem. So when you pass the prompt, the LLM generates a probability distribution over responses. You want to select the responses that satisfy some constraint, formal constraint. But that's not enough. You also want to maximize your task specific utility, right? If I ask you like, what is the fastest way to get to Denver, right? You can give me safe response. The safe response can be drive at 1 km/h. That's not good, right? So we want to also improve the task specific utility. There are few heuristics people use, but we are looking for like more principled solution. So you want to constrain the search space, prune out the space that's violating, and then in that space search for the best answer. Now the goals here is that we want to be applicable to different LLM systems, diffusion, autoregressive agents, VLMs. We want programmability because for different tasks, if you want to maximize utility, the decoding algorithm or the generation algorithm should be task specific. You can't rely on a specific decoding. There are some heuristics like you should maximize alignment with the LLM output distribution, but it does not always give you the best task utility. So you should be able to do it yourself, and then you should be also able to synthesize agents, for example, with formal constraints. So that's something very exciting. The applications are code generation, math reasoning, where you can enforce that the reasoning follows certain constraints, and also you can use it for LLM safety. I'll talk about self-evolving agents. The challenges are that overhead is a problem, right? These companies, like there was issue with companies being worried about cloud using so many tokens. So if you say even thank you to the cloud, it checks it with, I don't know, 23,000 rules, and that's a big issue, right? So guardrails, it's not for free, right? So these companies use, I mean, I think they should be using in some cases formal checkers, but they use LLM as a judge or whatever, right? I think like for natural generation tasks, right, you can't do much with the formal methods, but for things like code generation, etc., you should be able to do better. The specifications are complex. You need to handle discrete computations, which comes from your decoding steps, strings probabilities, and the task utility sometimes is not even available. You can just evaluate it from some user example or feedback. Now, the key principle is that you want to keep track of the partial generation like we saw with Beaver, and prune out the violations, or you don't want to generate the full response and then do reprompting because it wastes a lot of tokens. You would like to detect the violation as soon as possible and try to correct this. As I mentioned, we also want to provide some primitives that people can use to design different decoding strategies for different tasks. And this comes down to, as I mentioned, as an optimization problem. You want to be in the space satisfying the hard constraint and maximizing the task utility. So then in this space, I think Shubham is here, he led the first work, which was enforcing syntactic constraint, grammar constraints on LLM generation so that it satisfies the syntax of a grammar. So building on that, the next work was itergen, which was enforcing semantic constraints, where you would check detection of violation. You will detect that a semantic constraint is violated, go back and try to regenerate something else, right? The next work here was crane, which was combining unconstrained generation with constrained generation. Constrained generation meaning like you are pruning the generation algorithm. So there was like some empirical evidence that if you do constrained generation, the expressivity of the model reduces. We show theoretically that is not the case. You can design a specific decoding algorithm that combine unconstrained generation with constrained generation to get good performance, right? So we have also done it for diffusion models, but the main thing I want to get in this talk is the new algorithm, which is meta decode. As I mentioned, for different tasks, they require different constraint decoders because they have different characteristics. And then you want to be able to handle different tasks, constraint type, and you might have some budget on how many tokens you want to spend. So this is the meta algorithm, which is going to be secret because it's ongoing at the moment. It does not use Meadows yet. So it uses the primitives that we have developed in terms of monitor, backtracking, and so on, to generate a program that represents the decoding algorithm. And you can see LLMs would be involved in generating this. And it satisfies given token budget. So this is the result. We are kind of we are comparing on GSM symbolic, which is the math reasoning task, with itergen, crane. I showed you. There's grammar. I think this is grammar aligned decoding. There's cars, that's more recent. So doing task specific decoding does help. The other thing we have done is this agency, which is enforcing LTL constraints on the sequence of function call the model generates. So even this very latest state-of-the-art models, if you ask, in this case, give me a social security number, the agents are going to generate a sequence of function calls. So even if you give all the instructions from time to time, and sometimes under adversarial pressure, they may violate some developer specified constraints. So the point is that if you ask a social security number, I should first authenticate you. So the agent needs to generate the authentication function call before giving you the social security number. But it does not always satisfy this. So here we have enforced this by designing an orchestrator. So why do these models don't work in this long horizon task is that because they don't have any notion of a state. They don't know what is the state of external tools. So they made a call, they think it succeeded, right? And if it did not succeed, sometimes they don't track that information. So you would see all these I think, leaks or bugs done by these agents just because of this region. So the key ideas here is that we have a domain-specific language that makes it easy to express temporal constraints. Cloud can also do it. And then we have an orchestrator that keeps track of the external tools. We have a state representation and also what the LLM is doing. So as soon as we detect that it's generating a function call that violates a specification, we will reject it and try to regenerate something else. So this improves the performance over GPT-5 and Cloud Sonnet 4.5. The good thing here is that we not only improve safety, which is measured by conformance, it's always going to be 100%. That's the good thing about formal methods. But the utility also improves, right? So people say that, okay, formal method you will not improve this frontier models. That's an example where we actually do improve. And the adversarial is the setting where this is benign, is like we are not asking the model to violate. And in adversarial, we ask the model to do something bad. So conformance is again going to be 100, and this unconstrained generation is not good. The difference between conformance and harm is that how often does it conform to the specification, and harm is like if it violates the specification, does it do something bad, right? And similarly for this as well, we improve both utility and conformance. So the last thing I want to talk about is this notion of auto agents, which is getting very popular. So because LLMs can generate code, so why not write agentic programs where you have LLMs wrapped inside a code, can be if else, whatever, right? So that's the new paradigm of auto agent. So here the user will give some task that the agent should perform, and this task may require like calling multiple tools, like fetch this information from here, call this tool, or do whatever, right? So you would have a planner LLM, which is usually a more capable model. It will generate a program, right, which would represent a query specific agent, right? This also improves efficiency. In many cases, the smaller models with this query specific agent can perform better. So then this query specific agent, which is a program containing LLM calls, is going to execute on user input and then give it the response. So that's the paradigm of auto agent. Now you can go from auto agents to self-evolving agents if the program, the agent that you synthesize, has tunable parameters that you can tune on user specific task. So if the user gives you for their specific task some data set, you can actually tune the parameter of this program, right? So in this program you would have multiple LLM calls, and you can tune their parameters to be more aligned with user task. But you want to ensure safety. You want to ensure formal constraints. So a lot of work exists, but they don't try to enforce safety constraints. So that was the problem I just mentioned in terms of cheating. The problem looks like this, right? So again, the user provides you some behavioral spec that should hold end-to-end on the agentic program, right? Precondition, postcondition. It gives you some task information and the soft objective, the task specific loss function that your agentic program needs to like improve utility on. You have a set of library functions, you have a set of parametric models. These can be different LLMs, different neural networks, whatever. And you are given a data set on which you can compute the loss function. You want to ensure for all inputs the behavioral spec is satisfied while minimizing the task specific loss, right? So you want to synthesize a program that combines the parametric model and the library functions, right? Such that you can solve this constraint optimization problem, right? So the key thing compared to what people do is the enforcement of this hard constraint. So the program should be doing this. So this is the most recent work. It's called Severa. So there are two main components. So we use a planner LLM to generate an agentic program, and then this planner LLM decomposes the behavioral end-to-end specification into local contracts over individual function LLM calls in the model or any generative models that you use, right? So we use Daphne as the verifier to check the behavioral specification. So the planner LLM, it generates a program, and then we check if it verifies with Daphne. If it not, give the feedback and regenerate a new program, right? So the key component here is that in the agentic program, we will have this specialized notion of FGGM, which is formally guarded generative model. So the idea is very simple. It's just an if and else statement. So the planner LLM is going to give you local contract for each model, and you will use that local contract to construct this FGGM. So what happens here is you would give a prompt, and then you would check if the local constraint satisfies on that input or not. If it does, then the planner LLM will also give you a program, an output to return according to the program you have synthesized. If it fails, then you will have a fallback program. So we are relying a lot on the ability of the planner LLM, right, to be able to synthesize a program with these constraints. But because we have this if and else, and then the behavioral spec is decomposed at the local level, right, we can ensure that the end-to-end specification holds. Now the key thing here is that you want to evolve the agent. So each local agent or local LLM call, you can fine tune on the data, but you need a reward function for this. So the reward function we decompose as the probability of satisfying the if check, right? So you want to tune the model parameters FP there such that when you get the Y from the output, the check succeeds. So that allows us to decompose the task specific loss over individual LLM calls in the agent. Yeah, so that was the key construct where you would have each generative model call to a local formal contract, which would be this construction ensures that no matter what is the parameter that is used inside the model, the contract is always satisfied, and that gives you the reward signal. So this would be some examples. These are fairly complicated code, right? So this is just some small snippet, and even here the planner LLM can also optimize the prompt that you give inside the agentic program, right? So these are fairly complex agents. And for Daphne annotation, what we are measuring is also like where and notice, which means there is no cheating, versus where only. And then Severa without constraints, if we don't enforce the hard constraints, we get much more performance if we enforce the constraints, right? So 97% or 89.1% on Daphne bench. Also, like, we can improve the performance of agency I showed by self-evolving the agent. So if we just use agency as a fixed agent, now we can use this construct to also evolve, change the parameters to be more aligned with what we want. So if we do that and we synthesize a self-evolving agent, Qwen 3.8b outperforms Cloud Sonnet 4.5, right? GSM symbolic as well, this Severa, the point is that you are really tuning the agentic program for the task while ensuring hard constraints, the performance improves. This is the task I like as well. This is symbolic regression, where you're given a data with some amount of noise, 5 or 10%, and you want to infer a function that best fits the data. But you may have some domain specific constraints, like the function should be monotonic or whatnot. So that you can't ensure with just LLM prompting, and that's why when you try to look at this state-of-the-art methods, they violate the behavior, the function they synthesize violates the behavioral specification. And the right-hand side, we are measuring the performance, and compared to baseline, we are also more precise, right? So not only we satisfy the behavioral specification, we are also more precise. I think we'll not have time for the defense, but actually we have the strongest defense against pre-filling attacks for open source models. We use interpretability because just doing data augmentation like kind of adversarial training does not generalize much. It's more better to look at the representations the model produces and try to regularize there. I think there's a fascinating thing that that we can do, and I don't want to go for perfection. So there's this gap. People who do proofs or theoretical machine learning proofs about LLMs, they do very simplistic assumptions like one layer transformer and whatnot. Then there are other spectrum where it's like very empirical prompt, whatever generation, right? I think my aim is that I actually like this interpretability research the most, to find some axioms that may not be perfect, but that empirically capture, like kind of safety laws we have found for scaling laws, for these representations that these different models produce, and then use those axioms to prove properties that hold on a more realistic formal model of LLMs, not like the idealistic assumptions, right? So yeah, I mean, I wanted to advertise also the PLDI paper we have. So this is going to be on 17th, the first day. So going back to abstract interpretation for neural networks, now we can just construct PyTorch implementation using all the machinery we have, by if you just start from natural language prompting. So we have an LLM based approach that can actually synthesize sound abstract interpreters for neural networks. I think, like, for one more thing I wanted to emphasize is that for LLMs, I think the kind of math we have is also not very good. It's just based on those standard assumptions like linearity, convexity, and blah blah blah, right? Maybe we need to find better structures, better nonlinear assumptions that allow us to handle or reason about these more complicated computations that we have, right? Maybe LLM can do it, I don't know. And the other one is like evolving, where we are using gradient based optimization for like abstract interpretation, numerical program analysis. So during my PhD, I spent a lot of time writing abstract interpreters, like 10,000 whatever lines. Now we just have one algorithm that works for all domains and for any kind of combination of linear or non-linear arithmetic, right? So also the thing is that we all, for handling this LLMs, etc., we need to better ways to reason about non-linear computations. So I'll end with that and open to more questions. I like that expohedron thing that we have coming up, which is for probabilistic programs, a new nonlinear abstraction to reason about density functions. We also have some work on RLHF, mechanistic interpretability there, and some more neurosymbolic stuff. Thank you.
Yeah, I think we're out of time
Okay.
for questions, but if there's like a quick question, maybe that's okay. Yeah, or we can just
Okay.
find you.
I hope everybody wants to use formal methods after this talk.
Yeah, thanks for the amazing talk. Verified code reasoning by LLMs.
Okay. Hi everyone, my name is Meghana. I want to clarify that this work was done when I was interning at Google before I joined DeepMind. So today we're going to talk about the first step towards verified code reasoning by LLMs. I think a lot of the motivation was covered by Shubham, but I'll go over it again. So a code reasoning question comes up during a lot of software engineering tasks when you're trying to understand code bases or trying to do bug fixing, which I think at this point a lot of software engineers are using. And people are using LLMs to do this, and we want to see how we could verify the output. So a code reasoning question could be, why is this particular variable null here? Or it could be, is there a difference between using a switch and if-else-if statements? This comes under, I think it comes under the PAgE equivalence that Shubham was talking about. And today we're going to focus on these, I call it program equivalence problems. So what's a program equivalence problem? We want to check if two programs are semantically equivalent. In general, this is undecidable, but we're going to focus on minor local changes between these two programs. And though they're minor, they're still useful and they're very important in our daily software engineering tasks. So in this case, for example, if you take a look at both the code snippets, there is one primary change, that is this, in code 1, there is a call to a has value method, and in code 2, there's a call to an isEmpty method. Now the query you would ask is there a difference between using a has value method and isEmpty method? Now so a code reasoning agent would be, we use Gemini 2.5 Pro here with tools such as cat and find to answer these questions. That is, the code snippets and the query are given to an LLM. You can think of this as an equivalence analyzer, which uses its tools to analyze and then gives you a response. Now, LLMs are known to hallucinate, and we want to use formal verification techniques to validate the reasoning of LLMs. To do this, I want to first show you what a code reasoning agent would give you the output on this question. So for this is the agent output, which says that they're equivalent. And it gives the reasoning as to why the code snippets are equivalent. When we actually looked at the ground truth, we saw that both the code snippets are not equivalent because both the function calls are actually not semantically equivalent. So we noticed that the agent makes incorrect assumptions about the library functions and aggressively concludes that they're equivalent. Now, it doesn't extract the relevant functions, as Shubham also mentioned in his talk. And even when I provided the functions in the context, we noticed that the agent still concluded them as equivalent and did not care about the context that was provided. So we want to catch such hallucinations. So we can think of using formal verification tools as some sort of verified thinking, post hoc verified thinking. And to do this, we use a formal representation of the following. The first is agent claims. It's a formal representation of the agent's output, the explanation that it gives. Code semantics, which is the semantics of the underlying code snippets, and a verification condition, that is the formal statement of the code reasoning question that we're interested in. So in this case, it is that the code snippets have to be equivalent, or the program equivalence is the verification condition. So what is program equivalence? In our case, we consider program equivalence as for the same initial state. If the final states of both the programs are equivalent, then we would consider that the programs are equivalent. So to verify this, now that we have three representations of formal representations, we would say that the agent's explanation is correct if the code semantics implies agent claims, that is agent claims, the agent's claim is consistent with actually the code semantics, and the agent claims satisfies the verification condition as well. The first one is essential, but we're not covering that here. We're going to focus on the second part, which is, does the agent claim satisfy the verification condition? Okay, so how do you extract this formal representation? We use this 2 to 3 step pipeline. The first is where the partial code snippets are given to the agent to analyze whether the code snippets are equivalent. And it would give you a relevant code snippet. So it would do some implicit slicing. It would give you the relevant code snippets and also an explanation. We use the relevant code snippets. We send it through a formalizer, which is an LLM formalizer, which to get a formal representation, and use this formal representation against a verification condition in the formal verifier. So for this, we use Souffle's data log syntax as the formal representation. It's a declarative programming language that can be used to represent essential properties of the program and reason about it. So for the formal representation, we use, we want to extract the predicates for code 1, both the code snippets, code 1 and code 2, and the correspondence between the two programs, and also the explanation now using the predicates. So it's a little more formal language than was done previously by the agent. Okay, a simple example of what a data log example would be you can write your own predicates and your verification condition. You can define rules on your predicates, and then you can check these verification conditions that you have written against the set of facts or the predicates that are generated by the agent. So the code predicates, we want the code predicates to capture program dependence graph. So we borrow ideas from the PL literature of program equivalence, where two programs are equivalent if the program dependence graphs are equivalent. So they represent data flow dependency between in the programs and the control dependency. And we also capture correspondence. By that we mean there can be textual differences or statement mapping differences between the programs. We want to capture that as well. So the predicate list would look something like this, where we want to capture data flow dependencies. So whether we want the agent to output whether any variable has been defined at a particular in a particular file at a particular line, or if it's being used. There's a data value flow from a particular statement to another statement, and if there's as you can see, there's a control dependency of one particular variable on. It depends on a condition with a particular branch. We also model functions as unary and binary functions with the function symbols and the arguments of the function. So these essentially capture the data flow and control dependencies, thereby the program dependence graph. We also use, like as I was mentioning, variable mapping, whether a variable x in code 1 is similar to variable y in code 2, and so on. So these predicate list is given in the system prompt, and the agent is asked to generate these predicates for the current code snippets. And I also want to mention that this may not, in our implementation, we notice that this is doesn't generate all the predicates at once. So we query this, sample this 5 times, and then try to get the entire predicate list. So for this example that we were looking at, how do we model this line number 80? We have a unary function. We can define this has value method as a function symbol has value, and a session as the variable, and this is a unary function predicate in our predicate set. For code 2, this would be a unary function with an isEmpty function variable and a session as the input variable. A correspondence would be input and entry and exit mapping. So these predicates that we have are checked against a verification condition to check whether the predicates actually satisfy the verification condition, which is program equivalence. So when we define the verification condition rules in Souffle, given these predicates that the agent generated, we observe that the code snippets would be not equivalent. Because in our verifier, if two function symbols are not equivalent, we mark them as, conservatively mark the programs are not equivalent. Now this is conservative and you can make it more precise, but the point is that using this verifier, we can at least cache that the code snippets were not equivalent. In our implementation, we observe that it's easier to check not equivalence than actually checking equivalence, and that is how we defined our rules so that we can actually capture the not equivalent conditions. So in our experiments, we took 20 problems, 12 from bound safety problems, which is a bound safety is a C extension annotation to prevent out-of-bound memory access. So when you actually add the bound safety constraints to your program, you need to alter the program slightly to ensure that it is compilable. As a result, you would be modifying the program locally and slightly, and you want to check that this does not change the equivalence, does not change the program drastically, it's still semantically equivalent. The other is CRQ bench. It's a code reasoning questions that is derived from internal comments. The questions would be, the questions that we selected out of the form, is there a difference between using this particular method or that particular method, or is there a difference between writing a particular code snippets and using switch case or an if-else-if case. And we want to check if the code snippets are semantically equivalent. One problem is our own creation, which I'll actually talk about. Essentially, we want to find out if the agent can correctly reason about these programs. So for the benchmarks that we had, we can divide it into these 4 categories where the agent's response and the ground truth are equivalent or not. So in our cases, we haven't observed any false negative cases, but that's not to say that it doesn't exist, but for now, we do not see any false negative cases. We observed 9 true positive and true negative cases. That is, the agent's response is consistent with the ground truth, and our verifier can also adhere to that, saying it can say that whether the agent's response is consistent with the ground truth. It gives a yes or no certificate. There are 6 false positive cases that the agent concludes that the programs were equivalent, but the ground truth says that they were not equivalent. And I'll give you under what categories these fall into. So this is the incorrect assumptions about library functions that we were talking about, where it assumes has value and isEmpty are equivalent, and then concludes that the program snippets are equivalent. The second is it makes assumptions beyond the provided code snippets. So for example, these 2 code snippets would be equivalent only if the calling context would actually handle the return function, handle it properly. So the agent does not reason about how the calling context reasons about the return properly and concludes that they're equivalent. So such assumptions may or may not be correct, which was not tested by the agent. And this is another example where this is the one of our creation where we swap the AND condition, and we observe that agent hallucinates and claims that they're equivalent even if when they're not. So when we actually use these predicates that we were talking about to model these programs, we can check using a verifier that these two programs are not equivalent, whereas the agent claims that they're equivalent. And as a result, we can actually catch all the 6 false positive cases. So there were other examples as well where our analysis is not sufficient. That is, let's say there's a switch case and an if-else if case. Both cases are equivalent. The agent also terms it as equivalent, but our verifier terms it as incorrect. This is because our predicate analysis, as we had shown earlier, does not capture this switch and if-else if equivalence, and we should ideally be using more richer and precise analysis for this. Another case where we observed this is these two programs are equivalent, and it's just a matter of this dot value which actually returns the same fetcher value. These two programs are ideally equivalent, but the agent concludes that they're not equivalent because it doesn't look at the function value which actually returns the fetcher. And the verifier also misses it because it conservatively marks it that this function symbol and the other function symbol are not equivalent, and as a result they're not equivalent. So better prompting or better analysis, more rich analysis can help alleviate this issue. So then the idea is that we can you can formalize we want to formalize the agent's output so that we can actually check it in a verifier. In this case, 6 out of 8 such cases we're able to catch, and with better analysis we can do better, hopefully. And there are also current limitations such as the static analysis, limitations of static analysis for a data log, but you could maybe try and use better verifiers and maybe better predicate design. There are other interesting ideas of using this to implement iterative revision loops, where you can use this to better prompt the LLM to get you to notes. Sorry about that. Okay. Okay, that's the end of the talk, but just give me a minute to fix this.
Hi, I was surprised that you didn't get any overly conservative outputs in the positive and negative chart that you showed. I was also wondering that the definition of program equivalence may have varied granularity. For example, sometimes program equivalence may be defined only by the output equivalence of the function.
Yes.
So do you have a way to gauge this granularity?
I think for now we consider, like, if the variables are equivalent, if the program states are equivalent at the beginning, and if all the variables that are alive at the endpoint are equivalent,
that
then
might be too conservative.
That is true.
Definition.
Exactly. That I agree with that. I think you may want to, like, I think the idea is to show that using this verifier is helpful. Better analysis, better definitions can be used.
And the ground truths were also computed using the same definition of program equivalence.
Yes. Yeah. That's right.
Thank you.
Yeah.
Hi, thanks for the talk. I also questions about the risk of being over-conservative. Why did you choose the data log approach? Do you have some scalability concern in mind? Because I think this approach is really good for scalability with the data log solver, but you only show us very small functions. Did you use this approach for large functions, or was it always at small scale? Yeah, so our analysis, I think we've seen that they go up to like 20 or 30 lines of program. Our analysis, like, we did not do analysis where it spans over like hundreds of lines of programs. Okay, so and then did you consider some approach like equality saturation for checking program equivalence? Using e-graphs and technique like that, because I think they will subsume what you have done in terms of reasoning. That's a good point. I think we could try that. I think one of the reasons we considered data log was
I wish I could turn this on, but so when we were asking, so when we tried to formalize, okay, great. In this step, when we're using this formalizer, we also wanted the agent to output an explanation using these predicates, so that it's easier to check. So when an expression would look like there's a variable defined, and as a result I'm using the use predicate here, and there was a def predicate here, or there was a flow from variable x to variable y, I'm using the flow predicate. So we wanted that kind of textual output, and I think Datalog was helpful in doing that. That was one of the reasons of choosing Datalog. But for more rigorous analysis, I think you can use better verifiers in the backend.
So I would have tried testing first. So I would just imagine throwing a test harness that captures equivalence of the two programs, throw a fast tester at it, and I would imagine that that performs well. Did you try it? Do you have an ablation study with respect to that?
Yeah, no, sorry, we did not try that, but that is one idea of doing that.
Okay,
yeah.
I didn't see it on the future work, so that's why I asked.
Okay, so you know, like in Soufflé, like Datalog, you can examine how a particular claim is derived from the available statements, right? Like if you're saying I want to see how like path from A to C is derived, I can see it's derived from edge from A to B and then edge from B to C. Have you checked whether that kind of a formal kind of construction aligns with the internal thinkings of LMs? Like if LM is able to derive this, does it agree with the Datalog kind of proof construction?
I think in cases where it gives output correctly, it was aligned with it, as in the way I was talking about, there's a flow from variable A to variable B, and there's a flow from B to C, and as a result there's a flow from A to C. I think it captures this in its reasoning, and which is consistent with the Datalog rules. But in cases where it hallucinates, it just comes up with its own, like, it misinterprets the predicates and tries to justify its final conclusion, and that does not align with the Datalog rules. If that answers your question.
Sounds great.
Yeah.
Okay, thanks a lot,
Okay.
Meghna. So the next speaker is not available online yet. So we'll move on to the fourth talk, which is now the third talk, by Guido Martinez from Microsoft Research, and he'll talk about the next frontier for AI-generated kernel correctness.
All right. Can you folks hear me okay? Yes. All right. Hi, thank you for coming. So yeah, I'm going to tell you about correctness in AI-generated kernels. So I suppose everyone here has heard about GPUs. GPUs are running the planet these days, so running all of our agents and doing all of our experiments. And they're very hard to program. They are essentially a coprocessor to the CPU. They have a different memory. They have a very parallel structure. They have different memory hierarchies. They have complex synchronization. In GPU kernels, you also need to think about optimized math and memory transfers, and things are really complicated. And when you make a mistake, like an indexing error or you have a data race, you can start getting wrong answers. Your kernels can be non-deterministic, and it's a really difficult place to work on and debug. At the same time, there's a lot of interest in agentic programming of kernels, as for many other fields. So to gauge whether agents and LLMs are able to generate GPU kernels, recently there was there's a set of challenges called Kernel Bench. It's about 250 PyTorch functions that you have to implement in CUDA, and they're a way of measuring whether a coding agent can actually come up with CUDA implementations of these operations, and how fast they can make them. So the game is to make them as efficient as possible. That is the cute logo from Kernel Bench. And current models like Opus 4.6 or whatever, or 8, now pass Kernel Bench easily. They can code up all of the challenges, at least to get a passing solution, and then they can make them more and more efficient. At the time of the publication of Kernel Bench last year, this was not the case. NVIDIA, after a couple months after the paper was published, I think, NVIDIA reported that they could pass level 1 very, very easily. But what about correctness? So people are generating these kernels and they're measuring them and trying to make them faster. But we feel the attention has been mostly on the performance of the kernels, and correctness has gotten comparatively little attention. The correctness bar for these kernels is usually the same. You test them with a bunch of random inputs, and you accept them as good if they match some reference implementation on these random inputs and within some tolerance, because there's floating point everywhere in these kernels. And you could say, this is usually testing cannot guarantee correctness, of course, but you could say these kernels are usually kind of regular. Is testing enough? So the first claim we're making here is that tests are not sufficient, and we find several failures in the kernel bench test suite. So we find buggy kernels that pass the test, correct kernels that do not pass it, and also just cheats that you can completely sidestep the challenge. So as one illustrative example of a buggy kernel passing, one of the challenges is implementing a softmax function. And it turns out it's only tested on one input on a very large matrix that has about 400,000 columns, so the rows are very large. And by doing some mutation testing of correct solutions, we found racy kernels passing this benchmark. So you just remove barriers, and your kernel is obviously incorrect if you think about it, but it still passed the test. You can skip some of the outputs. You can just not write them. You can write everything a bit too far, and you can even actually just memset it to 0 in this case and still pass the test. So this was a surprising example. And it turns out that just this test is particularly bad because it's the rows are so large that the denominator, and that's the definition of softmax, the denominator is so large and the numerator is so small that these are very, very close to 0, way below the tolerance. So it's like, this test is just really bad. And then, adding more randomization helps, but it's difficult to think that you would completely get rid of these things. We've also found correct kernels that fail when they happen to be adding things in some different summation order from the reference implementation. So there's a challenge number 4 in this test suite is a matrix vector multiplication, which you can also think is just a matrix multiplication. And if you just take the textbook implementation of like the naive mathematical definition and you run it, you get a failure that says you're off by 50. But you're off by 50 from the actual result. And it turns out that torch.matmul, which is the reference, just uses a different order. And then if you change this textbook definition to do something called a KN compensated sum, a technique that reduces error, then you pass. But this is really the same algorithm mathematically. It's just one of them is, you were just far from the spec. And in this case, you could say that the spec is actually doing the better thing, and that is the thing you should compare against. But we found other cases in level 2, actually, in some more complex examples, where a better algorithm with less numerical error fails the test because the reference is just bad. So in a way, you're just comparing 2 floating point numbers, and you don't really have an idea of which one is the right one. Even more problems is just reward hacking. This is reported even by the kernel bench authors that the LLMs are just trying to make you happy and trying to pass the test, and they can completely sidestep the challenge of whatever you're asking them to do. So for instance, this setting the output to 0 can pass softmax, and it's also a question of how much you trust your LLMs, because you would have to review all of the code to make sure that they're not doing anything like this. They can definitely insert, if you don't trust them, they could insert a Trojan that you will never catch with testing. And other things that the kernel bench authors have found is that, well, you ask the thing to do a CUDA implementation, well, it doesn't do that. It just calls PyTorch, which is the reference, so it obviously passes, but it's obviously not the challenge. There's some funny mistakes also, like just a kernel that does nothing happens to have uninitialized memory that matches the reference run, so that also works. But it's pretty difficult to defend against all of these things. And we don't think that testing is the right way to do it. So what is the right way to do it? Our proposal here in this paper is that we can have AI-generated, AI-verified GPU kernels that come with a proof of correctness once and for all, and you don't need to test them. So we propose to verify things statically over the whole input space. You don't need to have test many distributions or whatever. And we're thinking about memory safety, data race freedom, and functional correctness. And then the trust, the thing the human has to review instead of the entire code and the dependency graph, is just the specification. That is basically the source of trust. To do this, we propose using Kuiper. Kuiper is a verified GPU framework built on FStar and Pulse. It gives you memory safety and data race freedom as table stakes. You cannot write unsafe kernels in this language. And it also allows you to state and verify precise functional correctness. And then Kuiper code extracts to plain CUDA, and then you just compile them as usual with NVCC and you run them. And it's also highly reusable. You can define highly reusable kernels and kernel components. There's a high degree of polymorphism. And if you want to learn more about Kuiper, the paper is in this PLDI, so you can come to our talk on Wednesday about it. I won't say much about the language itself, actually, but what I will say is the high degree of polymorphism is important. So just to give you a taste, this is a slightly shortened implementation of a gem in Kuiper, but it has very precise pre and post conditions and invariants and etc. And if you look closely, this is well, actually, never mind. But you can write this over any type, and so polymorphically over any type, or polymorphically over any layouts, and polymorphic over any operations that you want to do. So you verify this thing once, and you can extract just plain usual CUDA code that does the matmul, but you can also extract many more variants, but you only pay for the verification once. So we're going to make this verified language the target of the generation to solve the challenges, or to get your kernels. Compared to other approaches like Proofwrite, which is also recent and also targeted kernel bench, we're not trying to verify random or generated CUDA code at the level of CUDA. We're verifying something higher level and then generating the thing that we want. So then we check everything before the CUDA even shows up. The CUDA does not exist if the thing is not verified. So to do this, we just set a swarm of agents to go through the entire level 1 of kernel bench, 100 challenges, and read the implementations, understand them, and write a Kuiper kernel that implements that. To begin with, so usually verifying is more complicated than just writing a kernel. You need to think about the invariants, you need to think about precise pre and post conditions, you need to call the relevant lemmas to help the prover discover what you want to prove. So to make this process a bit more efficient, we split this into two tasks, two phases. The first phase is to implement a Kuiper kernel for the thing we want to do, but without really verifying anything. Just basically, the only thing you're proving is that it's memory safe and data race free, and it generates some executable CUDA code. And then we run this against the kernel bench framework to see if it actually passes the test. Once we have this, which is a relatively quick signal and it's relatively cheap, then we can think about verifying. And in the first stage, the agent is allowed to admit proofs that it thinks are hard for the moment, and then just test it to see if we're on the right track. And then when we have confidence that we're on the right track, the phase 2 goes to do write a fully precise functional spec for what you're doing, add the invariants, add the ghost code, add the lemmas, and iterate until you have a fully verified working kernel. And in this, here's also a place where it's important that the language is constraining what you can do. And whenever you're about to do something that is unsafe, the verifier will say, no, this line I cannot prove that it's safe, so you should go and fix it. And the agent can go and loop and spell out the proof in more detail. So with this framework, and using Claude Opus 4.6, we've obtained solutions for all of level 1 of kernel bench that pass the test suite. They are all verified in Kuiper, and they have fully precise specs, like the spec guarantees that they're implementing the mathematical operation that they claim to be implementing. And 100% of the code is verified GPU. There is no unverified CUDA in the mix. There is a slight amount of unverified CPU code to just bridge between the testing framework and the CUDA, and the verified CUDA coming from Kuiper. And this was written almost entirely by LLM agents. So this is very feasible. Like we did not need, with the current capabilities of LLMs, we did not need like a complicated setup. This was basically one Copilot session, very, very long Copilot session, but it was one session where we just talked to it. The human, in a way, was just architect, reviewer. We decided if things looked good enough to take. We also, one important thing that we had to do is tell the model to reuse previous results and follow a consistent style instead of just basically biving it, and use the polymorphism that you have to make reusable components, which otherwise it did not do on its own. And here the language was very important, actually. There's a big set of challenges where they all follow the same structure in this level 1 of kernel bench. There is a map that takes two matrices and overwrites the first matrix with some combination of the first one and the second. Then there's a reduction, usually by rows. Maybe you add all the rows, and maybe first you square them or something to compute like mean square error or something like this. And then there's a small final post-processing that you do maybe per element or maybe on one final result. And one of the advantages of doing this in Kuiper is that each of these stages is a super generic, highly polymorphic function that you can just call, and then you can just reuse. So each of these things took some effort, especially the tree reduction, which Jonas over there was the original author of. But once you have these, and once they're genetic enough, you can just compose them very, very easily. Some of the challenges are around 60 lines of pulse code, which is really not much at all. So yeah, the per kernel work, the per challenge work is relatively small. The heavy lifting is in this shared library of general combinators that you can use. And some of these existed before we attempted this, but some of them were added during this work by prompting the agents to do so. One thing I should say, since I was speaking about floating point, is that Kuiper allows you to verify floating point in some approximate notion. So it's really difficult to give concrete error bounds. So what Kuiper is doing is giving you this idealized relation between floating points and real numbers, and you prove things via this relation. So for instance, when we talk about a parallel reduction, like adding all of the elements of a row of a matrix, the post-condition you get is that the result is a correct approximation of all of the sums of the matrix. And this could be in any order, this could be in any associativity, be in any commutativity as well. So for instance, the challenge I mentioned that was fixed by the k-n summation, both the failing one and the passing one have the same spec. So the spec is approximate in the sense that it does not really, we do not and cannot really prove concrete error bounds, but it gives you a spec that is very, very composable. So for this particular issue here, one has to keep in mind that a fully precise spec does not really tell you much about the concrete error bounds. But what you can do is you prove this precise approximate functional spec, and then you go and check numerical error, go and call your oracle. And if that fails, you see how you can fix this kernel to keep the specification but be numerically better. So what was harder in this? A couple lessons we learned. So reward hacking is still possible, even though we are checking that they're not admitting proofs or something. It has happened that when they cannot prove something in Kuiper, the agent will just go like, oh, I'll just write a CUDA wrapper for it, and it just defeats the complete purpose of the experiment. But with some review and some also like very explicit indications to the agents, this was minimized. Also, that the library was the cause, not each kernel. These genetic combinators were really what made this possible. And also that some obligations that were really structural and tedious, they resisted automation. They were very difficult for the agents to perform. But thankfully, most of these are very low stakes or something we could fix manually after. So just to conclude, testing cannot certify kernels. We don't think this is a very viable way of certifying. Proofs are now practical, like all of this, 100 different challenges, which is mostly completely automatically performed. We think the languages are key. Like this is only possible because the language is giving me all the guarantees, and I only have to review a small bit of the spec. When I see the agent does something funny that I don't like, I can go and say, hey, go and refactor it, and then if it does and the specification is preserved, then I'm happy enough. I don't need to review every line of code. So trust mostly to the spec. So things we want to work on next is in making these things more performant, making the agents more reliable, and better at writing code without many iterations, and internal formalization, by which I mean giving you a way of reviewing the spec in a principled way. Yeah, so that's all. Thank you so much.
Thank you. How did you teach the agent the Kuiper language?
Oh, they learned it. So I think they have some knowledge of F-star, because F-star has been public for a while. So Kuiper is built on F-star, and there is the pulse separation logic on top of F-star, which is relatively recent. F-star has a long history, like 15 years maybe, though it's changed. So I think they have significant knowledge of F-star, somewhat less knowledge of pulse, and basically no knowledge of Kuiper, because this was not even public at the time. But they can infer what they have to do.
So you did not even give any reference documents about the language. This was just the verifier feedback, the agent learned the right Kuiper.
I think examples and verifier feedback. I don't know. They're so autonomous that I don't actually know what they did. They could have pulled the FSAR and Pulse book. There is a book online posted. I suppose it's in the training set. Some version of this book is in the training set. But as far as Kuiper goes, I just told they figured out, they're in a repo and they look at examples, and verifier feedback is super important. And the fact that they can grab and find to see what they can do. Yeah.
Sorry.
Hi, Shipadi Pai, University of Rochester. I know performance is your next goal, but I was just curious, what is the performance of your current L1 kernels compared to maybe the best?
Yeah, we haven't measured much of these actually. We were just concerned about correctness. I think they're not doing a lot of the fanciness, and the optimization techniques are baked into the combinators, which some of these existed before. So I suppose some of these are relatively performant. Like there is a tensor core gem implementation that is using some challenges. This is relatively performant. It's in some GPUs it's competitive with kubeless, and the softmax implementation I think is also relatively performant. But I don't have numbers I can show you. Yeah, sorry.
I have questions about the trust you give to the spec.
Yeah.
So first, what are the size of the specs for these challenges? And also, do you have examples of situation where the agent did something wrong with the spec? What kind of bad things did you?
Yeah, I have a couple. I think the rough size of a spec is, well, they usually look very similar, and like there's a function with a bunch of parameters, and it says if I have all these conditions on the input, then there's this condition on the output. And that condition, then you need to see how it's defined. I would say usually it's between 20 and 30 lines, maybe a bit more. Well, if you count the dependency cone. That's also the thing. For instance, one of the first challenges is a batched matrix multiplication, which means I give you an array of matrices and another array of matrices, and you give me an array of the products one by one. And then the first thing the agent wrote was, oh, I'm going to take an array of b times n times k and an array of b times k times n, and the result is this thing. And it just defined the product again, basically, which the product for matrices of 2 dimensions already existed, but the one for 3 did not. So in that case, it was like 100 lines, and I couldn't make sense of it. So my indication there was like, no, do not do this. Go and use the spec from here, and this is the way this should look. And then when you do that, it's really small. It's like this matrix 3 on every index, it's the product of the other 2 matrices, and that I can understand. It's like 2 lines. Then about hacking, one thing I did find is that sometimes the post condition would just be true. They say, oh yeah, whatever, this is future work or something, and they make some comment about it and they just leave it like unimplemented. Yeah, so those 2 things happened, I think. I should say reuse is important not only to get the kernels, but spec reuse is also important so I can understand it, because I know a bunch of components, and if they reuse it, that's easier.
Yeah. Hi, Sangeeta Chaudhary from AMD Research. Very cool talk and very cool work. So how scalable is this approach? So maybe it might work for kernels, small kernels like GEMS and GEMP, but nowadays trend is towards mega kernel where entire forward pass is fused into one kernel. So how do you see applying this approach to mega kernels?
Yeah, I'm not sure a completely autonomous approach would work to do like a super performant state-of-the-art kernel. But I think generating the components, so we can generate components in a way also that they sometimes can be fused. So if you just generate a wide array of components and you have some algorithm in design that is just fusing some parts, I think the agent could very well put them together. But we haven't reached here. In a way, the point of this paper was also to, well, figure out if this is possible at all. I suspect it's not true that the agents will just like knock it out of the park for like state-of-the-art kernels, at least today.
Very nice talk, Guido. Yeah. So I've been trying to understand bugs that have been reported in the PyTorch repository. And for anyone interested, I have a catalog of 90 bugs and so on. I've been trying to work on them. And we also have built a binary instrumentation tool in our group just to look for NAND bugs because these are some of the most widely reported. Mm-hmm. It's very eye-opening to actually see an LLM in action, so you can actually prompt a biomiss trial or anything. Produces pretty good answers for whatever diseases you utter. But inside, it generates 100 billion NANDs. So there, you can see actually in the code base X not equal to X in many cases, and we know why it does. It actually traps NANDs and then resets it to convenient values. So I don't know what the logic that these kernel writers follow in handling NANDs, except they do. Otherwise, the outputs will be corrupted. Mm-hmm. So I suspected, my suspicion is that kernels are not very composable. You might verify kernels for specific input ranges, but there is no guarantee that when you compose them, these ranges won't be blown. So they had to fix the NANDs. So I suspect this is a point of action for the community, for people assembled here, saying how can we really make this composable and specifically also build a good set of tools like you are building to inject these kernels back into PyTorch and see. Yeah, that's a meta comment. And,
so I totally agree.
Yeah.
I totally agree, and that's these specs about floating point that we provide, they're approximate, but the point is that they're composable. That's why I like them, because I can compose them. But they don't catch against NANDs. Yeah. The spec does not guarantee that something does not become a NAND or an INF. We cannot do that without bounding ranges and doing other reasoning. I would say that's probably better for like a second passive verification, but I don't know yet.
Yeah, anyone interested, write to me, ganeshutah@gmail.com. Yeah, I can send you what I collected. Yeah.
Thank you for the talk. So the spec that you're using, it must be written by human experts, right?
No, they're also written by agents, but we review it.
Okay. I recently read a paper where the authors were mentioning that the agent did the right thing, but the spec was incorrect, and they were updating the spec based on the agent traces. So I want to know, in your experience, did you come up with did you encounter such scenarios where you termed that the spec was correct, but then later you realized because the agent gave you the...
I think given this two-phase thing that we were doing, that's unlikely. Like, the agent comes up with a spec after it knows that it passes the kernel bench suite, which is not a big guarantee of anything, but at least you know that it's not completely broken. I don't think I found any wrong specs, actually, the fact that they're actually wrong. What I did find is that they're written in a style that I don't like, or they're like not reusing things that I would like them to reuse, or they're like 100 lines longer and then I can't review them. This I did find, but actually incorrect I don't think I found. Yeah.
Thank you for your talk. I had one question. Do you also formalize do you use inline PTX in your kernels?
No. Yeah, we don't have that yet.
And you cannot support it because you cannot provide the specification?
I don't know if we cannot support it, but today Kuiper does not allow it. I think maybe something you can definitely do is probably, if we extend it, add inline PTX and just assume that this thing has a spec. So it becomes something you trust, but at least you could do it. Then formalizing PTX and their semantics, I don't know if this is tractable at all. But if it's even well understood, I think probably not. Yeah.
Thanks for the talk. So I have one question over the kind of the polymorphic aspect of the element type. So I see you have array 2 and the element type may be a shape. So how does that? So how do you handle different floating point data types? Like, would the same thing works for FP32 also work for like BF16, FP8, and that kind of thing? And in order to understand like how good your modeling of the floating point error is, have you tried like removing the part where you run the kernel bench correctness test, but directly go to verification and see what's the proportion of things that you can verify, but actually fails the floating point test?
Right. I think you had two questions. So one is, yes, we can do any of these types. And as far as the real reasoning go, they're all equivalent pretty much. You just get that, basically if I have that A approximates real A and B approximates real B, then the sum at whatever width approximates the real sum. And this is what you get. And there is no notion at all of error. So all of these algorithms, numerically, they could not be way off. There's no numerical, I should say maybe there's no numerical guarantees. So then about if they pass, but can you verify it and not pass the test? I think if you do softmax, but you do not normalize by subtracting the max, this will definitely pass in Kuiper. Because subtracting the max in the reals is like a no-up. It doesn't do anything. But numerically, it will explode. So that would be one example. I didn't run the agents on this loop, but I'm sure they will find such examples, yes.
Okay, yeah. Let's thank the speaker for answering all the questions and for the amazing talk.
Thank you.
So next we have Brendan Coyne from Boston University presenting testing LLM-generated distributed protocol code. Are there any questions? Yeah.
Given that these protocols are mostly known, before. Given these protocols are mostly known already, right, by humans, how do you know that they did any work and not regurgitate whatever humans knew before?
Well, that's a good question. I ran it multiple times for each LLM to see if it would give like a certain like class like for. So for like for example like the ring election the goal was that like given my network class like with like these three functions the register the send and receive my goal was to see if the LLM could create just one class. I gave were just be able to issues. Some of them could, some of them could not, especially for tougher ones. So at least for the RAF consensus, I don't think, at least for what I was doing, I don't think the LLMs are create one.
Okay, thanks.
Yeah, did you give them a harness or any tools, or was it just?
No, just the network class that I created. That was it.
Okay, let's thank the speaker. If there are no more questions. And I think that's the end of the morning session because, yeah, one speaker didn't show up. Thank you. Okay, welcome back everyone for the afternoon session. The first talk of this session is by Hiroyuki Katsura from University of Cambridge. And he'll talk about combining agentic AI and lightweight formal methods to find bugs in a production hypervisor.
Yes. Thanks for the introduction. I'm Hiro. This is a joint work with Kevin, Marian, and Peter Su. So basically, this talk is about like combining agentic AI and lightweight formal methods to find bugs in a production hypervisor. More precisely, what I did is like we asked OpenAI Codex to write executable test specifications in the ambient language following the framework by Memarian et al. And then for the Android PKVM hypervisor. And then we found several amusing bugs. But probably this slide doesn't make sense to you until we explain this part. So I would like to start with talking about what is writing specification in the ambient language first. The high-level idea here is that, like, what we want to do here is to write nice specifications. And the specification and implementation is a sort of two different redundant views of the things, and then tensioned against each other. And then especially if you only have an implementation with no specification or with some very prose specification, what do we do for this? One possible thing that we can do is to do some formal verification, and then this is actually good if you can actually do this successfully, because you can get a very strong guarantee about the implementation. But the thing is that even in the era of LLMs, especially retroactively verifying something is very difficult. And then possibly that brings us to thinking about combining lightweight formal methods and some LLMs. And then this can be tensioned by testing, and by the nature of the testing, obviously the strong guarantee is going to be less strong. But still, it is easy to do, so why not we do this? Basically, in this talk, especially, we focus on executable specification proposed by Memarian et al. Last year. This is basically about writing ghost code in the ambient language. Here, the implementation of C can be seen as a sort of manipulation of the concrete implementation state. So if you run the run the function, then you can manipulate for example, heap or global variables. And then actually the implementation contains a lot of unnecessary details, right? For example, if you think of them hypervisor, then they will sort of deal with some device drivers or low-level stuff. They are unnecessary to specify the intended behavior. And in that sense, what we want to do here is to sort of abstract away unnecessary parts of the implementation, and then you can get some ideal abstract state from the concrete state. This can be done by an abstract function. Then we write some specification to specify what is going to be the intended behavior of the function. Then we compare the result computed from the post state of the implementation, and then if there is a discrepancy between these two, then we can say, okay, the specification or implementation should be wrong. The good thing about this work is that everything is in C, so we don't have to have any additional methodology or framework or infrastructure to achieve this work. This is particularly important if we want to verify the hypervisor retroactively, because hypervisor involves some very complicated C programs or some low-level stuff, and then we cannot deal with nicely in the formal verification even now. Especially we use some PKVM hypervisor, which is an Android hypervisor developed by Google. And then the good thing about this Android hypervisor is that it is widely deployed already. And probably if you have an Android phone, then PKVM is definitely running inside your phone. The goal of the PKVM is to enforce the memory isolation property between guest virtual machines and Linux kernels, so that the guest virtual machine can handle sensitive data such as fingerprints secretly. And then even when the guest Linux Android itself is compromised, we would like to make sure that this fingerprint will not be leaked to the attacker. And in order to enforce this kind of property, it should be sort of a hypervisor. And in that sense, it's going to be a very, runs at a high privileged level under the Linux kernel. And also, everything is mostly written in C, and probably plus some assembly. And these kind of things make the verification particularly difficult. And then that's why we want to consider some lightweight method, especially executable specification for PKVM. Here, for example, if you take some page table, then page tables probably are implemented in three manipulation things, right? So if you want to, for example, if you want to update some page table, then definitely PKVM needs to deal with some low-level stuff like updating some registers or like deal with some device drivers like a MMU or such kind of. But in order to specify the ownership structure of the page table or such kind of, these kind of things are unnecessary details. And in that sense, we can think of page tables as a finite maps, like from U64 to U64. And then to this end, to achieve this kind of abstraction, we actually implement an abstract function, which is sort of like a walking the concrete page tables, and then builds the finite maps from that. Then we can write, on top of these kind of abstract states, we can implement the specification functions. This is the idea of executable specs for PKVM, which is proposed by Mimarian et al. And then in this work, actually, we ask AI to write this kind of specification in C in this style. This is what we did. So now this slide makes more sense to you, I guess. And then now we would like to talk about what we actually did, like what kind of agent we implemented, and then what experience that we have. First of all, the agent that we implemented is called like exec-spec agent. And then this is basically on top of like just a codex, OpenAI codex, composed of like tons of prompts. It is composed of 300 lines of initial prompts, 10 different agent skills, and then some like knowledge base of how to write some executable specs. The entire pipeline looks like this. First of all, we ask AI to find an appropriate place to be verified. And then we ask AI to actually write a ghost code. After that, we also ask AI to write the test cases and then run the test cases with the executable specs. Then, if there is a discrepancy between the implementation and specification that AI wrote, we also ask AI to debug this discrepancy. If this discrepancy comes from the specification side, then we can just ask them to refine the ghost state, ghost executable spec. But if that comes from the implementation side, then we can definitely need to sort of triage the bug. And then if it's considered to be very serious, then we can just report these kind of bugs to the developer. That is the entire pipeline. And then to achieve this, we have sort of included several important skills. For example, definitely we have to teach AI how to write executable spec or how to write nice test cases. Or possibly, we would like to say, okay, how to build the hypervisor or how to run the test machinery. And also, we have included several artifacts that previously humans developed. First of all, the target binary, like a target Android Linux kernel is Android Linux kernel version 16 with kernel version 6.12, which is the latest version of the Android. And then we have included 3 previously developed artifacts, which is, first of all, manually written executable specifications for the previous version, which is kernel version 6.4. And also we have included PKVM proxy, which is a kernel driver to invoke hypervisor calls from the user land so that we can write test cases as like normal user programs. Also, we have included another machinery, which is called PKVM proxy OCaml, which is an OCaml wrapper to write some test cases in a declarative manner in OCaml. The first thing that we did is to like sort of ask AI to comport these kind of machinery to the latest version of Android. And the results are actually surprisingly promising to me. First of all, what we did is like we ran this agent for about a month with like a single ChatGPT Pro subscription plus a single human, which is me. And then for the first 2 weeks, we sort of tuned the agent. Then after that, we sort of run the agent autonomously for about 2 weeks. Then the agent finally, in the end, like wrote 1,700 lines of 1,000 lines of ghost code and some hypercode test cases. And then more interestingly, they could find interesting bugs in PKVM. So far, the agent found 6 confirmed bugs, and then 4 of which seem to be serious. And then everything has been already fixed by Google developers. Especially, particularly interesting thing is that some of the bugs are sort of a logical bugs, not like a memory corruption, user after free or buffer overflow, not that kind of bugs. And then that bug, that is more like a memory breaking some property which is called memory isolation property. Here, PKVM is protecting the property or called memory isolation property, which is physical pages are never shared between Android Linux kernel and guest virtual machine unless they are explicitly shared. This kind of property is particularly important to protect the sensitive data, because in the earlier slides, I said like, in order to protect the sensitive data, we have to say like, even when the Android Linux kernel is compromised, we have to make sure that this kind of sensitive data will not be leaked to the attacker. And in order to do this, what we want to do, like what PKVM is doing, is that like physical pages will not be like shared to the guest virtual machines unless it is explicitly shared. So if you can break this property, then obviously this is going to be leading to the leak of the sensitive data. So let me briefly explain what is page table and ownership so that we can give you some sense of the bugs. So basically, there is a sort of, in the Android, we have physical pages. And then what we want to do here is that like, we have host Android and the guest virtual machine. And then PKVM is maintaining these kind of page tables so that all the physical pages are owned disjointly. Here, host Android uses these blue pages, and then guest virtual machine using these pink pages. And then host Android kernel can map their virtual address to the physical page that is owned by this host Android, but we cannot map this virtual address to the address that is owned by other virtual machines. Okay. And this is basically what PKVM is doing to ensure that like memory isolation can be achieved. And then even when we would like to move the memory to the guest virtual machine, you cannot just copy the map to this one. And instead of doing that, we just first give up this mapping and then add a new map like this. And by doing so, we can transfer the ownership nicely, right? And then what we found is that by exploiting the bug that agent found, like we can create this. We can create the situation where, like, both host Android and guest virtual machine can point to the same physical page simultaneously without some intention or some like accidentally. And then unfortunately, this is sort of still under security review. So in that sense, it might be not good to talk about in detail about this bug. So I can just say this kind of brief overview of the bug. But still, it is particularly interesting because it's not like a memory corruption, but it's more like a logical bugs. And then still, by using some specification, I believe that like this kind of specification can contribute to finding this kind of bug. And unfortunately, this is sort of ongoing work, and in that sense, I have to say, like, it is unclear whether it is actually it contributes to like finding bugs more effectively or not. I mean, so it is possible that LLMs are just clever enough to find bugs. That might be possible, but still, what we want to say here is that there are some observations that we can defend. First of all, actually, at first I did like, please find bugs in PKVM. Like this kind of thing I first did. And then unfortunately, this doesn't work because it will report so many like a subtle, small issues. And then we will be easily overwhelmed by a lot of like false positives or a lot of like subtle issues. Also, defining the bug like in PKVM itself is very difficult. Especially like, effectively, when can you say like the ownership like a discipline is violated? This kind of thing cannot be easily detected, unlike memory corruption or segmentation fault, that kind of things. And finally, writing specification itself is a good thing, even when there is like no bug. And especially, I think this point is particularly interesting to us because in the near future, definitely agentic AI and formal verification things are more and more common. And in that future, we believe that what's good for humans and also should be good for like AIs. And then essentially, if you want to apply like retroactive verification to the existing artifact, I believe that like all or nothing verification will not work. And then instead, what we want to do here is to sort of first apply executable spec to like extract the intended behavior nicely while finding some bugs. Then after you have enough confidence about the implementation and specification, then you can move on to more like a formal specification. And more, so in the end, we can probably do some formal proofs by using that specification. And at least what we have is that this works at least for humans. And then on Wednesday, we will be talking about this kind of work in PLDI. So if you are interested in this talk, probably this talk should be also interesting to you. And even though this is done by humans, like a lot of manual efforts, but we believe that this kind of process also can be accelerated by AIs. So I would like to conclude our talk. So what we did is that like we ask AI to write executable specifications, and then that was actually promising because we could find a lot of interesting bugs. And then furthermore, I would like to emphasize that writing executable spec is a sort of a good on-ramp towards the formal verification. That's it. Thank you.
Thank you. So in your work, you had specifications from a previous version of PKBM.
Yeah.
What is your sense of like if that did not exist, would the agent be able to write reasonable specifications?
Yes, I have reviewed some of the specifications, and then some of the specification actually wrong, and also sometimes the porting from the previous version to the new version sometimes wrong. And in that sense, not all the specification looks correct, but still it contributed to finding bugs actually. That is probably the correct story.
Yeah, thanks for the talk and nice work. And what I don't understand is, so you obtain using AI this abstract specification, which is executable, and so, but the specification is written by AI.
Yes.
So what does it mean to find a bug in the specification then?
Basically, so the specification is sort of enforced to be sort of mathematical manner, right? And in that sense, like if the implementation is like a, how do I say, like a specification is sort of a very abstract item of the implementation. And the implementation itself is more like a verbose, and then there are many lines of code. And in that sense, specification itself is going to be sort of the like a compression of the implementation. And then if you ask AI to write this kind of abstract notion of the implementation, probably at some point in the future, the AI will find some path that there is a sort of discrepancy between the abstract notion and implementation. And in that case, instead of like just directly fixing some specification or just fixing directly the implementation, we ask them to triage what is going to be the problem. And then through this like a sort of process, if AI is clever enough to like detect what is going to be wrong, then it actually can report some like a sensible bugs. That is the story of this work.
Yeah, I understand the vision, but I don't understand on this particular 4 examples. How did you find them by generating the spec yourself?
I mean, by generating the spec itself. One thing that I have to emphasize here is that like thinking about specification itself is a good forcing function to like find bugs. And some of the bugs can be found through this kind of thinking about specification. But one bug that I have found is like sort of, maybe I need to, one bug that we found is that like there is a sort of donation ownership transfer function, which can be transfer some page to another page. But there is another function which can be which can transfer several pages at once to a different virtual machine. And this kind of thing should correspond to each other if you try to iteratively do this kind of batch work, right, by using this hypercore. And then what AI found is that if you try to do this in a batch, you can get this observation. But unfortunately, if you try to iteratively do this kind of work by using the single hypercore, sorry, I'm using some standard hypercore, then there is going to be sort of differences. And then this can be explained by using specification, because we are using the same specification, sort of the same specification for these two hypercores. And then we will notice that there's a sort of discrepancy between these things by abstracting away some unnecessary things in the implementation. And in that sense, we can sort of extract some common parts of the hypercores or common sense of the hypercores. And then by doing that, actually, AI could find some bugs. And actually, I wanted to talk about this bug more precisely and more concretely, but still it is under review. So in that sense, it might be not good to talk about that. Sorry.
Okay, thanks, Hiro.
Okay,
the next speaker is Tyler Sorensen from UC Santa Cruz. And Tyler will talk about experience using agentic workflows to debug complex GPU compiler stacks.
Let's see, I think it's on. I think it's good. Okay, cool. All right, so thanks everybody for coming. Like Shraddha said, I'm Tyler Sorensen. I'm going to be presenting our use case using agentic workflows to debug complex systems. We're calling this from workaround to root causes. So the lead authors here are Abhijit Ramesh. He's a master's student working with me at UC Santa Cruz. Reese Levine is a PhD student working there. Unfortunately, neither of them could make it, but I will take any opportunity to brag about the students' work that I can. So that's why I'm here. And kind of before we get started, I want all of you to take a look up from your laptops and go here. Here's a nice QR code. Do it on your phone if you're able to. I mean, if you're able to do it on your laptop as well, let's see. So I'm going to give you 5, 4, 3, 2, 1 to go. And if you went there, you're going to see this page. So this page, what's going to happen, and let's see if it works, because this is on the hotel Wi-Fi. We're going to have you download a small LLM. So this is about 200 megabytes. Let's see if we just totally crash the hotel Wi-Fi. I have it cached on mine, but what's happening is I downloaded this local language model, and I am now creating some text. I've asked it to summarize LLMs on my phone, and you can see that it's doing text. So this is the Gemma model, and I can ask it some more questions. I can ask it about llama.cpp, which is an inference engine. If I click this, you can see it's going to start giving me text there. And so what's interesting about this is that this is happening all on my laptop. This is not calling out to a server like we see with Anthropic or OpenAI. My laptop, I'm running Windows. I have a Qualcomm GPU. You know, it's maybe not as fast as we might like, but this is happening all on my machine. And if you went to this website and if you were able to download that model and press that button, you should get similar text. Probably not the exact same text, but you would probably see something similar. And this is what the students in the research group have been working on. They've been working on getting this LLM inference working in the browser so that I can come into this room and have anybody pull this up on their laptop and phone and execute LLMs on the edge, and you don't even need the internet. If you were to go on the top of the Rocky Mountains, this would work. And we think that's pretty cool. Now, where's my mouse? There it is. Getting back to the slideshow, the fact that this worked for everybody in this room, we have so many different GPUs, systems, people have Android phones, people have Apple phones. What actually happens? So We all know that LLMs execute on the GPU. So if you're going through the browser, that's something called WGSL. So it's not CUDA. CUDA is NVIDIA's kind of private thing. This is a more open source GPU language called WGSL. So that's what the GPU language is written in. Now, depending on what your favorite browser is, you went through Chrome, Firefox, or Safari. And so now you have 3 different browsers that we sort of have to deal with. On top of that, because people can't play along nicely, each of those browsers has their own GPU engine. So Chrome has something called Dawn, Firefox has something called WGPU, so on and so forth. And again, because this world is kind of so diverse, depending on your operating system, now you're going to another GPU framework. Apple has Metal, Windows has DirectX, and Linux has Vulkan. So in this room, we probably went through paths of all these different things. You end up at your driver, which is going to be different for every GPU we have. People here probably have Apple, Qualcomm, NVIDIA, AMD, and finally you end up at the GPU. This is a crazy complicated stack, but it has allowed us to do that really cool thing where all of us can run a local LLM. I find that to be very cool. Now, what happens, however, though, is if anybody's kind of worked on these different GPU frameworks, you know that there's sort of bugs lurking in all of these things. And in fact, my PhD supervisor, Ali, in 2017, they did a bunch of work basically showing there are bugs all over all of these stacks. And so, because these things are kind of so fragile, and in fact, it might have not worked for everybody in this room, and if it didn't, come talk to me. But you can imagine when you're dealing with a fragile environment like this, you might open it up, on Safari and you ask for a story about turtles. It works very well. Same machine, you open it up on Chrome, and this is not a very compelling story about turtles. In fact, this is a bug. And again, if you've worked on big software systems, your stomach will just sink when you see this, because you're like, how do I even start debugging this thing? And to be fair, the people who make these stacks, they do work hard. The W3C committee and the Kronos group run massive conformance test suites over these things. It's a huge undertaking. But as soon as you start looking into it, just because this is such a diverse and chaotic landscape, there's so many exceptions in these, like vendors get exceptions, they don't have to pass everything. And again, about 10 years ago with my advisor, I wrote a workshop paper complaining about all the bugs that show up across these systems. So it is just extremely difficult. Ideally, in a perfect world, we'd like to take that bug that we just saw and we go through and we'd like to reduce it, localize it, find a nice little reproduction so that we can debug it. But is that actually what happens in the real world? And you probably won't be surprised that the answer is no. We had an agent go through the bug tracker of Dawn, which is one of these GPU engines that works in Chrome. We analyzed 500 of the latest bugs that were reported for Chrome, and what we found is only 10% of them had reproduction test cases. So people are reporting bugs. It's good. People should report bugs. But very few people actually are able to reproduce them and provide them with their bug report. And like I said, this is understandable given the difficulties. But what I'm going to do is I'm standing here, and I think with agents, we can take this 10%, and we should strive to get this to 100%. Agents allow us to do this, and this isn't just for these complex GPU stacks. This is kind of for any stack that we might have, operating systems, compilers, whatever. And agents are just so incredibly well suited to help us do this. Agents are able to really speak every layer's language. We've seen throughout today all these different languages that the agents speak. Very few people, if anybody has talked about writing a compiler or a parser, the agents just do that. The agents can compose tools across the stack. And the agents are just tireless. All the stuff that we hate doing, the tedious of trying this, does the bug appear? Trying this, does the bug appear? The agents just do that tirelessly. They don't take lunch breaks or sleep. So this is where I think we can get to. And the experience I'm going to talk to you today, I think it can serve as a rough roadmap. What we did is we were able to simplify this crazy bug in this deep stack to a small, about 20 lines of Metal code that caused this error in the Apple Metal compiler. And to get there, we didn't start off with sort of super well disciplined approaches. This was really just our experiences from the trenches. We did 3 long-running agentic workflows. It was 2 re-steering. We wrote custom agents. And we think that this is somewhat reproducible. So if you find yourself running into these crazy bugs, you might want to try something like this. So let's start with the obvious answer, or the obvious first step. So if we saw that bug, and if you sit down, you pull up your Copilot CLI or whatever, and you say, hey, debug this. Well, this interactive mode just fails, and Abhijit tried really hard. He worked for about 16 hours just having that chat window up and saying, hey, debug this, go find this, and you know, this 16 hours is kind of like total work time. He spent about a week on it, and just wasn't able to get anywhere. And this should probably sound familiar to a lot of people who have used agents. What happens is these big complex systems, the agent fills up its context, it tries doing things like browser flags, it tries it tries a bunch of things, but then eventually you see that dreaded conversation compaction show up, and then it just retries all of those negative things, and you end up not making progress. So in that interactive chat session, that really didn't work in this case. And I think this was Opus 4.7, yeah, so fairly recent. I'm just gonna keep an eye on the time. Okay, so then what happens? This didn't work, and as we were investigating why this didn't work, it's because the agent just kept retrying things that it knew failed. So when this happens, you just need to decompose the problem for the agents into more manageable chunks. And you can do this in 2 dimensions. You can decompose the agents, and you can decompose the memory management. And you know, to do this, we took our individual stack and we thought about how this actually makes sense in this web GPU world. So we think this idea of, we're calling them probes. I don't know if that's exactly the right word I want to keep, but you know, this AI image over here looks very intense. But rather than having one agent kind of go and get overwhelmed by this massive system, we have our different layers, and each probe, or each agent probe, is responsible for one level of that crazy complicated stack. And that agent has just said, hey, you focus on the metal, or you focus on the Vulkan, or you focus on the driver. Don't do anything else. And what this does is this keeps each agent's focus narrow, it knows what tools it needs, and it doesn't blow up its context trying to kind of do too much. So in our stack, what we did is we actually ended up writing 3 probes. You could imagine writing more as we wanted, if we needed to debug more. But we wrote a probe up here for WGSL. So this is able to write GPU kernels. It's kind of the foundational probe for this work. But what's interesting about these probes is how much time they actually take to come up with meaningful knowledge. If you're up there at WGSL, and if you need to run that to get feedback, you at least have to go through 2 compilers. You have to go through your browser compiler, and then you have to go through your lower level compiler. Now, another probe we had actually runs the browser. So this can be done through an MCP tool from Microsoft called Playwright. It will open up the browser, it'll run it, it's all very cool, it's all very slow. So this probe is extremely slow, but it's authoritative. When you have a bug, and if you need to reproduce it, you need to do it at the top of the stack, even if it's slow. But as you start to narrow the bug, you can make probes at the lower level. So we made a metal probe, which just knows how to run metal code, and that's extremely fast. You know, it just writes it writes a kernel in metal, it can compile it, execute it. And so what's interesting about these probes is they exist on a gradient. You tend to have higher probes at the higher level of the stack. They take a long time, but they are authoritative. Lower level probes can just iterate faster. And how you orchestrate these probes, I think, is incredibly important, and they can really speed up this whole process. I also want to talk a little bit about the memory management, because we said we decomposed agents into different probes, but we also decomposed the memory that each agent does. So over here, we have our kind of agentic workflow. So these agents, this is just a Python script that calls Copilot CLI with these different tasks. So the first thing you do is you just kind of initialize the system. You're like, hey, I'm getting a bunch of garbage when I run this LLM. And that initialize agent says, okay, well, I think I can roughly know a few things that need to be done. It creates a task list. That task list then feeds into the task selector agent. It's a very basic agent. It just says, hey, there's a bunch of tasks. Which probe is going to be best suited to do that? Can I do that with the browser probe? Can I do it with the metal probe? Or whatever probe you want to do. And so it localizes that task, hopefully to the best possible probe that is sufficient to do it. And then each probe creates a lessons learned, and this lesson learned creates kind of a library that the whole agentic system can look into and hopefully eventually reproduce the bug. So we did 3 executions of this workflow. The first execution found a workaround. It basically took the system, it patched the kernel, and it said it works now. That's not enough, so what we said is you actually need to come up with a reproduction of the bug that we can report. That one took 12 hours. The final one took 47 minutes, and that was actually taking that bug and say, hey, can you guess where in the closed source compiler the error actually was? So let me talk a little bit about the workaround. So workaround, even in this giant stack, tons of kernels running AI kernels. Basically, what we found is that it was a problem with integer division. We replaced integer division with shifts, and it fixed the issue. It started to work on Chrome. You might just say, yes, we're done. We can now do a cool demo at PLDI. But if we were a really good PLDI participant, we would know this paper by John Regier in PLDI 2012 about test case reduction that says a reasonable compiler user might easily decide that the most economic course is to find a workaround and not be sidetracked by the effort required to produce a small test case and report the bug. So we read that paper and we said, let's go get a test case reduction, and so we can actually report this. And what we found is that that division, if you just saw that, you would just call up the Apple people and say you have a problem with integer division. But it's really a little bit more complex than that. What we found is it wasn't just the integer division that was required. You actually needed a local array, and you needed to loop over that array, and in that array, you did the division. And that array needed to be a certain size. So this was the second long-running execution. We took the agentic workflow and we said, don't stop until you have a small workaround. And this one took a while. I'm going to talk about that in one sec. Finally, once we had that small test case, we said, let's push this even further. The compilers for these GPUs are closed source, but maybe we can kind of guess which optimization paths the bug existed in. And what we ended up doing is going down to the Metal code, writing a Metal probe. So Metal is Apple's GPU language. And what we ended up telling the agent to fiddle around with some compiler optimization hint flags like no inline, loop unrolling. And what we found is actually it needed to inline a function and it needed to unroll a loop for the bug to appear. So we were able to kind of go from this crazy bug in the full system to come down and say, we believe that we know the exact optimization paths that are causing this bug in the exact compiler. A few things to talk about is, again, in my mind, what we learned is it's all about these probes. So to find that workaround, it took 2 hours. It called playwright, that's the one that drives the browser 6 times, and WGSL probe 5 times. So that's kind of in the middle. For the reproduction, that took 12 hours. That's way too long. But you can see it called the playwright probe 60 times. And that's because in our agent instructions, we said, hey, we really need a small reproduction that reproduces this faithfully in the browser. So the framework said, okay, I'm only going to use a browser agent because that's what I need to reproduce. It's extremely slow to do that. Whereas then you go to the Metal probe, for that last one, it only called it about 4 times, and it took it about 47 minutes. So the name of the game here is to write your orchestration framework so that it can drive these tasks to the most efficient probe that's needed. And I think that is it. So yes, so what we were able to do is we were able to take this giant system, this crazy bug that otherwise in an academic program you might just say, sorry, if you have Chrome on Apple, you don't get to play with the demo. We were able to reduce it down to about 20 lines of code. We were able to essentially infer which optimization paths in a closed source compiler were responsible for that bug. And now we all have a demo that we can do in a room like this. And like I said, these are the students that are responsible for the work. Running local LLMs is really fun. You should go check it out. The students have done great work. And that's it. Thank you.
This is just a clarification question, but the workaround was in the WGSL code?
Well, so I mean, you start off in that huge. So yeah, the workaround was in the WGSL code. You switch the integer division with the shifts, but then that gets translated to the Metal, which also has done it, and you have that crazy stack that, yeah. And so then we wanted to reduce it as low in the stack as possible, so we knew how to report the bug to. Yeah.
Okay. Yeah. Thanks, Tyler.
Cool. Thanks.
So the next talk is actually a recorded talk. It's event-based design abstractions for agent harnesses by McCoy Becker. And they'll take questions like offline, I guess, because there was an emergency and the speaker couldn't make it.
Hi, everyone. My name is McCoy Becker. I'm a student at MIT's probabilistic computing project, and today, hi, everyone. My name is McCoy Becker. I'm a student at MIT's probabilistic computing project, and today I'll present a proposal. Hi, everyone. My name is McCoy Becker. I'm a student at MIT's probabilistic computing project, and today I'll present a proposal on event-based design applications. Hi, everyone. My name is McCoy Becker. I'm a student at MIT's probabilistic computing project, and today I'll present a proposal on event-based design abstractions for agent harnesses, a project we're working on with my collaborators, Matt and Fabian, and several advisors. Our work is non-archival, but is available, and we hope to release some agent software soon which implements our proposal, and which you'll see in a set of brief demo slides at the end. I'm going to start with motivation by walking through observations about the development of agents as software systems. I'll use agent and agent harness mostly interchangeably in this talk. An agent is a combination of ingredients: a language model trained to emit tool requests, which is then plugged into an event loop, which handles executing those tool requests along with other concerns, giving the language model an interface to interact with the external world. Now, agents today are highly complex programs. Systems such as Claude Code and Codex are growing features that have traditionally belonged within the concerns of programming languages and systems. These concerns include security, for instance, things like managing what tool calls an agent is allowed to make given the state of the environment or the world. Concerns like management of parallel subagents, which are independent agent instances that go off and do work alongside other instances. Concerns like planning and memory. One thing which you'll notice is that these concerns cross-cut over each other. Security, for instance, is of course important when subagents are running around a code base working simultaneously. So there's a big interaction of the concerns here. Any particular agent implementation often has to confront this interaction in some form. These systems have to answer for the management of these interactions in the design of the software. The other thing which is true about agents is that they became popular extremely fast and recently, which tends to imply a bit of a mess in terms of organization of concerns. As a collective, we're writing and experiencing these systems and programs for the first time. If you analyze the architectures of recent agents, you may notice that they may be complicated in terms of code organization. The source code of a version of Claude Code was leaked in March of this year. You can download a version of it and analyze the architecture. One thing you'll find if you do some lightweight dependency analysis of the code base is that that version of the system takes an approach to cross-cutting interactions of concerns, which amounts to sort of just letting the system reach all over itself. Now, the Claude Code team has been proud of dogfooding the system by allowing Claude Code to mostly write itself, which is extremely impressive, but also makes it tough to understand at what level this organization of concerns is caused by developing model capabilities, which are still improving, or just the novelty of this type of program. One thing which is clear is that this type of organization is difficult for humans to understand. I want to quickly show a few meta observations about the development of Claude Code, just taking Claude Code as a instance of popular agent systems. Here's a plot giving a rough indication of the feature velocity of Claude Code. You can see how quickly this system has been stood up. It entered into the public consciousness about April to May of last year, and since then the team has been hard at work extending and improving on the system. This is very impressive growth. The red line here is the 3-month average of the number of features parsed out of the official changelog from Anthropic. Now, one thing you can see is that it's kind of growing like a traditional monolithic software system where the concerns of users are driving the feature expansion of the system and features keep being added over time. But one thing which is significantly different from what we might call pre-agentic software, good old deterministic software, is that agent systems and agents are probability distributions. The usage of a language model to drive decision-making turns the entire piece of software into a probabilistic program. This fundamental aspect of these systems means that no two users are going to have the same experience using the system, even if they are using it for the exact same tasks. Now, we already have difficulty. We already have difficult software development problems when our concern is making the red line go up for deterministic software. Agents are not deterministic. They are complex probability distributions whose behavior we mostly don't understand at this point in time. And now they're being exposed to things like sensitive data, being tasked with new kinds of computational problems of complexity that existing software just hasn't really attempted to handle or solve. This is uncharted territory, but the approach to development and the architecture of these systems has kind of been to adopt pre-existing norms of development. With that in mind, I want to focus on two aspects of these systems. The first aspect is observability. A big concern with agents is observability. These systems are now writing and shipping code into production. I mentioned sensitive data on a previous slide. Many people are learning the hard way that allowing autonomous systems to act without supervision is a double-edged sword. The question here is, if a particular agent session creates a bug, how do you track down the cause of such a thing? For instance, developing a root cause analysis for why the agent introduced the bug or made the mistake. This is of high concern to everyone, both users of agents as well as the labs who are making agentic language models via training. There has to be some sort of approach to understanding why these things occur. An obvious observation drawn from this concern is that new features into agent systems may be in conflict with understanding the properties of the agent probability distribution and may even impede reasoning about why agents cause issues. Each PR to the logic of an agent harness might change the distribution in some way. How do we know that the changes are good or are in the right direction to prevent the mistakes on the previous slide from happening as the agent system is developed? Well, traditional software has rich testing methodologies such as unit and property-based testing, as well as formal methods and verification. It's not clear that agentic systems have a coherent and cheap solution to the same problem. One technique might be to run the agent many, many times and see statistically, on average, if the behavior avoids mistakes. But as serving frontier models gets more expensive and difficult to do, the only companies that can afford to test their agents in this way are the labs themselves, which is unsatisfying for users of agent software who likely want control over their harnesses. Now, the second concern, which relates intimately to observability, is the notion of extensibility of software. Let's again return to this plot for a moment. These contributions shown in this plot are going into the logic of Claude Code as a harness itself. So each of these bars represents new or modified code inside the harness. Each new feature may potentially impact the behavior of the agent probability distribution induced by the harness and the agentic language model. The traditional test set, the traditional notion of a test set, just does not cover these changes to behavior. Now, it's not clear if this is being factored into the development of systems like Claude Code, but on the surface, this means that if we took investigating the effect of changes to agents seriously, each new feature is actually very expensive, much more expensive than traditional deterministic software. And the cost compounds as the harness grows to account for more concerns, because now we're trying to cover the behavior of a very complex probability distribution across an ever-growing surface of settings. The bottom line here, the big problem with agent software, is that we cannot treat agents and agent harnesses like normal software, because they are not. They are probabilistic software. And worse, the impulse, the development impulse to make agent harnesses more general purpose, cover more functionality, and do more things, is at odds both in cost and in understanding of the agent probability distribution induced by the harness logic and the underlying language model. That brings us to our design proposal, which is an attempt at reducing the concerns of the harness to a small core based on some functional design principles. And in addition, a call to move the concerns of extensibility into user space, not into the logic of the harness itself. Now, as agent designers, we desire a design that addresses these concerns in some sort of nice compositional way. In this talk, we propose a design for agent harnesses oriented around the abstraction of an append-only store of information, something that we keep track of and store as we use the agent. We refer to this data abstraction as an event log, following the event sourcing and reactive programming literature. The word durable here on this slide just means that we persist this event log for our session somewhere, in the same way that transcripts are persisted in typical agents today. This data structure, this event log, contains all the meaningful semantic events that occur in the operation of the harness. This event log is a strict generalization of the notion of a transcript, so it's not far from the sorts of data abstractions that we're already used to seeing in agent harnesses. Our proposal is to try and remove any semantically meaningful hidden state from inside the running logic of the harness and place it on the event log in a form which I'll show in a bit. Now, if we're able to do this, the immediate benefit is that the state of the agent at any point in time can be recovered via simple functional transformations on this data structure. In this case, say the event log is represented by an append-only list, any interesting intermediate point in the operation of the system can be computed by a fold over the log. Now, the problem that we have to confront to implement this design is that we must provide an approach to supporting all the subsystems and cross-cutting concerns and interactions that I mentioned earlier when talking about introducing agent systems. But now, additionally, we need some way to organize the state of the subsystems in the agent so that the subsystem state can be derived from the event log directly. Those subsystems within the harness are useful. They improve the capabilities of the agent through the harness, allowing the language model to interact with the world more effectively. So we want them. We want the subsystems. But of course, we want some way to provide those subsystem capabilities while retaining observability, modularity, and extensibility. To address this problem, we drew upon inspiration from the reactive and concurrent programming languages community. In particular, languages such as Lynda and Syndicate have deeply studied the question of communicating interacting systems. We draw upon one of their essential insights. We treat the event log as a communication medium between the subsystems that will make up the agent harness. Then we specify modules of functionality called facets. These objects, these facets, carry a set of methods within which we'll write the logic of the subsystems that we wish to support in our harness. The init method of a facet provides an initial state for the facet. The step method is used when the facet needs to fold over the event log to construct an up-to-date local state representation. The last two methods, emits and propose, are interfaces that provide the means by which facets can interact with the event log and communicate with each other. Propose allows a facet to offer an event to the log, and emits allows a facet to judge the acceptance of an event onto the log. These two methods are the basis for communication between the facets over the log. So what might a facet look like? Here's a locks facet, for instance, right? Perhaps our concern is that we want the harness to manage resources, such as files, and we want agents to request resources. We need some management system to deal with this. Here, the local state is a map from file resource identifiers to agent identifiers. The logic of the admits method for this facet is pretty intuitive. If an agent tries to claim a resource, a file, while another agent holds it, that event is rejected by this facet. Rejection by a facet means that, by any facet, means that the event is not admitted to the log. The propose method here is also interesting. Here, the locks facet publishes its set of held resources. This allows agents to view this event when they need to determine if a resource is free, to decide if they want to request it or not. How exactly then does the harness run if you have these facets? Well, the core of the harness, like all agent harnesses, is a sort of event loop. Here, external input comes into the loop and is pushed onto a queue, which holds all proposed events. The loop is then relatively simple. All facets are queried to see if the proposed event at the top of the queue is popped off. Then all facets are queried to see if any of the facets rejects the event. If no facet rejects the event, then the event log is extended with the event. The proposed event is committed to the log. And facets whose internal state changes in reaction to that event get to propose new events in reaction. Those event proposals go back on the queue, and the process repeats until there are no events on the queue. So our high-level solution here is that these various subsystems, these facets, will communicate using the event log. Now, despite this sort of new language, the process of communication is still analogous to the import couplings we saw earlier when we studied Claude Code. But now one benefit of this approach is that the semantic effect of communication, of this organization, can be isolated into a formal object, a sort of protocol between the interacting facets. This protocol consists of a set of events that the facets agree to exchange and the logic within the facets themselves that deal with things like how the facets react to the events. And what events they propose in response to events that they're watching for. Now, one point here is that though the agent is probabilistic, it doesn't really matter, right? The policy is to reject anything that any facet rejects, which means that the agent is safe under the facet protocol definition of safety across the distribution. So as long as one reasons carefully about the communication protocols between facets, those protocols can carry safety invariance, and no matter what the underlying agent proposes, the underlying agentic LM proposes in terms of tool calls or events itself, the overall operation of the harness retains these safety invariants. Now, just to end the talk, I'm going to transition to a few slides which show some visuals from a new agent system we're working on. This system is called a tiny agent. The implementation of this system was not described fully in our submission, but we took our proposal for this event log style of programming agent harnesses, and we blended a few other nice PL ideas to make a harness. We're preparing a larger work describing this system. In this harness, the underlying event log and the functionality of the harness itself is programmed using a Lisp language with support for reader macros and the ability to program the UI. In some ways, this harness is analogous to Emacs. The primitives that are exposed into the Lisp are just events that cause other facets in the system to do things, exactly the design described in the previous slides. The Lisp can cause effectful computation by pushing events onto the log, and facets that actually implement that effectful computation react to those events. So the base layer of this harness remains this durable event log with facets and communication protocols. Well, what does this system look like? It's just like your typical agent. You say hello to it and it responds. But how does it respond? Well, there's a Lisp function that is responsible for implementing the logic of organizing the context, sending it to the agentic LM via API, parsing the response and returning it back to you. But this response policy function can be customized in user space. This notion of using a Lisp to implement the harness logic that is exposed within the harness is our approach to the problem of extensibility. Now, this policy function can be inspected and modified from within the harness itself. And you can change how the agent responds by overriding the Lisp environment with new logic. Modifying the Lisp environment to change the agent means you can do all sorts of fun things. On this slide, it's a bit of a toy example. For instance, because prompt construction is just a Lisp function, we can modify it in the session. Remember, we're not leaving the terminal user interface for any of this. It's all modified in real time while you're using the system. Of course, if you want, you can save your Lisp code and load it as part of the bootstrapping of the agent. You can version control the code, etc. Here in this fun example, we edit a part of the response policy function to append, please respond to me like a pirate to all prompts. Our design here allows you to grow into the harness without leaving the harness. Let me say that there are harnesses that have approached the question of extensibility from a similar perspective. A system called PyMono is a really nice system that really pioneered these sorts of ideas in the space of agent harnesses. Of course, the notion of a system which is programmable from within is not new. It has a long history in the programming languages community. In our case, our system approaches the question of extensibility by presenting it as a capability, essentially a veneer around a Lisp interpreter that users get to interact with and customize while they're using the system. In conclusion, this was a talk about design proposal for event-based design abstractions for agent harnesses. A preprint of this work and some work that didn't make it into our experience report is in progress. If you found anything interesting, I'd be happy to answer any questions. Please reach out. My email is on this slide. Thank you.
Isha, you can start.
Hello, hi everyone. I believe there's some audio issue. That's why I couldn't hear anyone. I hope the room can hear me. And I'm assuming that as a yes. So let me start off. I'm Isha, and today I'm going to present our work, Lumos, which is a domain-specific language for frontier model systems certification. This is actually was mentioned by Professor Gagandeep in the morning keynote as well. So let's get started. We start with the premise that frontier model systems are not trustworthy, and this is witnessed by numerous examples shown in multiple works. So, this is one example that we have observed, which shows Gemini producing biased behavior. And in general, developers cannot guarantee whether their tools will produce the trustworthy responses or not, and for that, numerous evaluation methods have been developed. Another example from the recent vision language models is as shown here. When QuenVL is prompted for driving situation, it says that in the most obvious right turn actually, that the right turn should not be taken in the rain. And that could be unsafe for and cause phantom braking, etc. The traditional trustworthy AI pipeline has consisted of evaluating the developed and trained deep neural networks and constantly repairing or retraining them with the evaluation feedback. And prior works have shown that formal certification is a reliable evaluation, and in our work we have attempted to develop that for the large language models and frontier AI systems. The previous evaluation methods for these frontier models has been primarily based on benchmarking and adversarial attacks. And they have a lot of limitations, the key limitations being that they are limited to few test cases. They often have test set leakage as an issue, and there are no guarantees on the generalization of the results. On the other hand, on the related works on DNN certification, this field has traditionally been quite distinct from evaluating frontier models, and that has been because these methods are computationally expensive. They're also very customized to certain architectures, and the speed at which these models, like the frontier systems, are developing, the certification methods will find it hard to catch up if they are just traditionally just extended to the new domains. And they're also often restricted to very simple specifications that maybe are the local robustness kind of specifications. And here the initial ideas we had when we began to form a bridge between the frontier model system evaluation and DNN certification in our pioneering work LLM Cert. This consisted of the key idea of invoking black box statistical certification to ensure practical trustworthiness over realistic large distributions of inputs and provide high confidence probability bounds. An instance of this framework was also discussed in the first keynote, and these kinds of frameworks work on two key principles. The first one is on quantitative certification. We believe that if a quantitative reliable metric is important, and if it is supplied by statistical guarantee, we can be assured of the reliability of the metric and can be aware of the scope of its generalization. Further, a metric-based approach provides actionable insights to the developers, and they can take it as feedback to improve their models. In fact, in our follow-up work, we are actually using this kind of feedback to improve the models ourselves. Furthermore, we want a quantitative certifier to be also applicable to closed source models, because those are the primary and the state-of-the-art models actually. The second principle we desire out of these frameworks is also related to formal specifications. We want these to be over large input distributions as opposed to individual inputs. Furthermore, we want them to capture natural and adversarial scenarios instead of just very niche cases. And furthermore, we want them to focus on realistic properties like fairness as opposed to robustness or very simple properties. In our prior works involving LLM cert, we developed a family of frameworks concerning specialized properties such as fairness and reading comprehension. So the reading comprehension property was covered in the first keynote. The key shortcomings of these specialized frameworks was that it was very customized to the specifications. When we initially began to develop these frameworks, we were focusing on very specific properties, and we found it hard to generalize it to any arbitrary specifications. Hence, it is important to somehow find some kind of overlaps between these which were not apparent. Furthermore, with the advancement in multimodal AI, it is important to capture multimodal inputs as well. And most importantly, it is important to capture the validity of the statistical certification always. So we want the statistical certification we do to be valid at all times. For this, we have developed the first probabilistic programming language for frontier model system certification. Our language is called Lumos, and you can access the paper at the QR code. The core idea is around probabilistic specifications, and the objective canonically looks like as shown here. We want to assess the probability that if we draw a random prompt from a distribution, then the model response that is produced by L applied on P is judged as desirable by a response desirability judge. So with this objective in mind, the certificate we design is based on upper and lower bounds, such that the probability of the objective lying within these bounds is more than some user-defined confidence level. So it can be modulated by the user as per their needs. What we have observed in this particular work is that the key unifying factors behind all these distinct specifications involving arbitrary properties like fairness, reading comprehension, or safety is the fact that graphs abstract the prompt spaces in prior specifications. And I will show examples in this presentation to illustrate that. Our language has probabilistic specifications at its core, and it is developed out of text-rich graphs which are used for prompt distribution representations. So it's kind of like an abstraction of representing realistic prompts using graphical structures. And this language has native multimodal support as well. To formulate the prompt distributions, we start off with a text-rich graph and form a subgraph distribution on top of it, from which we draw random subgraphs, and to form the prompts, we templatize these subgraphs to natural language by using some programmatic operations. The key constructs of this language, as expected, would be graph elements, prompt elements, and random sampling of expressions. Let me walk you through an example of how we write code in Lumos, and you will observe that this is actually capturing a practical property within a unifying abstraction. So we focus on multi-turn safety certification, which is our latest work, which was published at ICLR 2026 and also deployed within Amazon's Nova evaluation suite. The focus in this work is on assessing the safety of the responses in a sequence of harm eliciting questions which form a conversation. And thus, this is a temporal specification. An example of such a conversation is as shown here, where the user constantly asks harm eliciting queries which could be adapted, but importantly, these should form a conversation and they should have coherent questions all the time. Sorry, is there a question?
Slides don't seem to be changing if you are in fact changing them. It's on slide 14.
I am on 21st.
Okay. Okay. I don't know.
Do you still see slide 14?
Like, would rejoining help? I don't know.
Should I try resharing?
Yeah.
Okay, 1 second. Are you able to
Okay,
see
yes.
it?
Yeah.
Cool. Yeah, let me know if this issue recurs. All right, so this is an example of a multi-turn conversation. So I believe I was on slide 14, but I was showing you an example of multi-turn safety certification. And essentially, I was discussing what this property is about. So here's an illustrative example for what this property means. We want each query in the conversation to be coherent to the previous conversation that has happened. And basically, the property looks like as shown here, where we assess the probability that if we were to draw a sequence of prompts from a distribution such that these are coherent, the LLM should produce safe responses at all steps. So this is how this is encoded in Lumos, and let me break this down for you in basically abstracting it into a graph abstraction. So we start with a graph of queries. So here I'm showing you a simple toy graph where we have individual nodes represent individual distinct queries which could be harm eliciting, and they are connected with each other by if they are semantically similar and disconnected otherwise. We declare a graph in this language and invoke this by a standard, by just having the nodes and the edges. Then we further invoke a statistical certifier by declaring the certification operation using the key construct estimate prob. So this also informs the interpreter for the language about the different parameters for this statistical certification. And here in this example, following the prior work, we have followed the Klopper-Pearson method of statistical certification, wherein we make n observations by making trials, random trials from the distribution, and we bound the probability using k observed successes in n trials. We obtain Klopper-Pearson bounds with 1 minus delta confidence, and the key requirement for the prior work was that we should have independent and identically distributed trials. Our language is inherently designed to make sure that such statistical validity is respected. Next, in our subgraph sampling operation, where the subgraphs canonically or abstractly represent the prompts or the prompt sequences as we might have, we start off in this example by sampling any random prompt or any random query corresponding to random nodes. So here the programmer has declared by a sampling operation over all nodes. Next, they declare that the next node should be connected to the initially sampled node, that is, it should be the neighbor, and thus should maintain the coherence criteria for a conversation. So let's say node 6 was selected, and in the next step, a distinct but a neighboring node should be selected, and for example, node 7 was selected. We can have this kind of a graph which we combine by sequential node sampling, and there could be multiple other options that could be generated. To form our prompt, we would format the individual elements of the graph within the prompt template. So in this very simple example, we just directly put the queries from the nodes into the prompt. But in more complicated examples, very diverse kind of templates can be provided, and we have examples of those in our paper. But here we basically see that a conversation is flowing by simple programmatic operations that we have defined on top of the graph. And eventually, we define the observations of the LLM responses using the toEstimate construct, which judges for whether the responses at each step were safe or not, or generally desirable or not. Safety can be judged by numerous kinds of judges. Here, for example, we use the harm bench judge on various different axes of safety. And in general, it could be like any judge model that could be invoked here. The probabilistic certification happens in a loop started off from estimate prob and ended by toEstimate construct, and it could be Klopper-Pearson or any other method. In our results, we see, like here I'm showing results for queries with cybercrime targets. We see very bad performance shown by these models, which are actually large and state of the art. And we see that these models have, so the lower numbers indicate that models are more safe, and higher numbers indicate that models display more attack success rate. So here we see that DeepSeek, for example, has more than 50% chance of being attacked and produce some cybercrime related content. Our language can certify numerous properties, and in our paper we show examples of all of those. We have temporal specifications, just like what I discussed right now. We have domain knowledge specifications, as in the medical question answering covered in the keynote. And we also have relational specifications concerning with fairness. And oftentimes, like, these properties may not be really graph related, but we can always create these encodings that like capture the graph, that actually are based on the graph and can still certify. Most importantly, the thing that makes me most excited about this line of work is that creating a language gives us a new way to think about specifications. So earlier, when we started off, we were actually absolutely clueless about how we should even begin defining these specifications. But now, having these constructs in our hands, we are able to manipulate them and apply them to very distinct properties and different models to actually create valid and reliable certification bounds. As an instance of this, like to demonstrate what I'm saying, we have created the first safety specifications for VLMs in autonomous driving for scenarios just like as you see here, where we can simulate weather and other kinds of barrier situations as well. So the way we encode VLM safety is by using scene graphs, which basically correspond to scenes. And these graphical constructs correspond to different entities in a scene and how they relate with each other. We convert these scene graphs to scenes by using standard tools like Scenic, which the PL community has developed. And utilizing these tools, we are able to actually produce certification bounds that show how unreliable these models are. For example, Qwen2VL is more than 90% unsafe, which makes me really scared. Here are examples which show the hazard in practice, where we see that, like this is the initial example of Qwen2VL not suggesting a right turn when it's obvious, and Lava simply ignoring the presence of a barrier because it's clear weather. In the next example, this was already kind of mentioned in the keynote, but just continuing and giving more details. Like if we were to integrate, we are able to integrate prompt level verifier Beaver over entire LLM prompt distributions as well. So if you just as a reminder for the audience, Beaver gives us sound probabilistic bounds for single prompt outputs. And we are able to combine these bounds for individual prompts over large distributions of prompts to produce certification bounds for these models that how privacy revealing they are. So here we see the aggregated Beaver bounds, which indicate that, for example, Qwen3 has like more than 24% chance of revealing the information. So, I mean, privacy, for example, may have lower thresholds because like even like a slight chance of privacy revealing might actually be devastating. So we see multiple examples of how the privacy failures are operating, and these models are actually pretty vulnerable is just in a nutshell, that's what I would like to say. So this was again slightly discussed in the keynote, but just to provide more details, we have followed up this work with a failure mode discovery framework, wherein going beyond these specifications, we want to find the ones that are more adversarial for the model and lead to higher failure rates. So essentially, this starts off by searching for failure modes, which correspond to conjunctions of concepts, realistic concepts that could occur. So here are like examples of concepts. For example, a cyclist in the picture and clear weather and a dumpster also in the surrounding. So for searching for failure modes, we essentially conduct a beam search informed by an acquisition function to obtain conjunctions of concepts that lead to high failure rates, and we assess these failure rates by our certification methods. And as examples, we observe failures where, for example, Gemini says that for a very close by cyclist in simulation, Gemini just says slow down, and actually that results in a collision in simulation. In summary, I have presented the first domain-specific language for frontier model system certification, which uses graphs as the key abstraction. This language has probabilistic certification at its core, focusing on graphs and actually provides insights that go beyond what was possible by previous evaluations. Furthermore, with the language framework, we are able to think more about specifications and are able to design and connect elements together to create new kinds of evaluations which were not possible previously. Thank you. This is our work is on the project page as shown on the top right, and also I'm on the job market, so please contact me at my email for any further information. Thank you.
Okay, thanks, Isha. I
you.
think we are over time, so if there are any questions, we can take them offline. Yeah.
Yeah, for sure. Please feel free to just email me with any questions.
Okay, thank you.
Thanks.
Okay, we'll just wait for the next speaker to set up, I guess. So the last talk of this session is by Lev Ioannidis from Microsoft Research. Unfortunately, it could not connect to the remote speaker. It's about lazy validation and self-healing for agentic programs. Can we switch to in-person? Like, yeah.
user there. With respect to policies. Principle, in this case I have PAgE, is we have this hierarchy of principles, and parental is the parent, restrict creates a new principle, which is then mentioned in the policy, which we can create a new policy. So both principles and policies are first-class objects in our language. Clinical trial. In this example, we simulate some patient visits, and then we go and do some data analytics on those visits. So first, blinded data, and we enforce to make an agent call with visits. We ensure the policies evolve as the agents kind of evolve. And finally, as I was saying, the field projection at the end is we have three different forms. We have schema, which is the type of types. We have workflows. It needs call side and make sure it type checks. If it doesn't type check, then we look back to the agent and say, with whatever error we got, check that those policies are satisfied. A firewall MCP that at runtime checks every tool call for policy satisfaction. Executing a prefix of the program up until we see an agent call, and then there is no user in the loop. This all happens as part of the the key idea here is that agentic programs will break and things will go wrong, but those issues at the point that they break and not have cascading failures. Why are cascading failures bad? You can say, well, an agent can recover from a cascading failure. Yes, but there is a high token cost to figure out if an agent will fail. So what we're doing is we use programming language techniques like type checking and well-formed checks to catch the error. column shows that there's next steps for PAgE is and we are integrating in GitHub agentic workflows to help reduce. To sum up, this
Thank you. Thank you very much. So maybe a clarification about the lean proof. What I understand, it's a formalization about a meta theorem about your language. You are not validating with lean proof the agent itself during the okay. And so what kind of validation are you doing for the agent? Because you mentioned static validation, but I did not understand what kind of static techniques you are using.
So the meta-theoretic result that carries over to safety of the agents is the preservation theorem. So every agentic output of this workflow will be well-formed and well-typed. So we prove this once for lean, and we get this for all the programs. Another property that translates to agents is this policy monotonicity property. So we have through restrict, which creates some principles, and enforce, which creates like even stricter policies. We have a mechanism to create some agents and restrict them in some limited capabilities. And we can verify that if we use this mechanism, then we can get stricter policies for evolving programs. Finally, we have the firewall MCP, which is only in implementation, verifies every tool call, but that's not part of the informalization. That's an implementation.
So when the model proposes a new schema, a new type, what format? Is it like a JSON format?
Yeah, so the type of types is a JSON schema, yeah. So in itself, that has a schema that we validate. But then after that is created, then we go and check subsequent values that use that type.
So what are the kinds of policies you support, like security policies?
Yeah, we support access control policies. So our actions are read, write for files and directories. So resources are files and directories, and principles are singletons that we create in the language.
Okay, thanks, Lev. Yeah. And thanks everyone for your patience with the AV issues. Yeah, this is a great session.